tutorial, so we'll see, we will continue. I also later will show you this slides, so even if we will not finish all, you can easily just run this PDF and check individual scenarios with MATLAB. So it is up to you. In case that you will have any question later, even next week and so on, just contact me through email or through WhatsApp group or anything. So I am available, there is no issue. So what about spectrum allocation? Of course, there is some global spectrum allocation. It is defined on big conferences, but you will not touch with them because it is like on national levels. So each country, I think almost any country in the world is participant in this spectrum allocation, except maybe few small countries. This global spectrum allocation put entire frequency bands from, I think, 3 kilohertz up to 300 gigahertz. So of course in this upper sides there is almost not any services. Why? Because it is so huge frequencies that until yet we don't have so many devices that working in this high frequency range. And what is important, in any service, in any allocation in frequency spectrum, we have always two columns. It is primary and secondary allocation. Primary, it is mean protected. It is priority. It is mean like GSM service. It is priority, and this like GSM service, some mobile operator has priority for this frequency allocation, for specific allocation, and nobody else can't use it. Then is so-called secondary allocation, and it is without protection. But there is one important thing: must not interfere with primary allocation. So, okay, secondary allocation can be used for some service, but can be conflict with primary allocation, if you get my point. So you can use it if you have permission, of course, but be careful, you can't involve this primary allocation. So definite globally, it is ITU radio regulation, so call it RR, and it is updated in WRC conferences. This ITU, it is International Telecommunication Union, is divided to many different sectors, but we are interested now only in ITUR, it is radio communication sector, and part of this radio communication sector is so-called Radio Regulation Board. And this regulation board consists proposing rules for the allocation in frequencies. Okay, there is from 9 up to 400 gigahertz, some tables are from 3 up to 300 gigahertz and so on. I think that this small differences is caused by national allocation table, because I know that British, they have it from 3 up to 300 gigahertz. We have little difference, so it is like varies, but never mind. In the 9 kilohertz there is not so many services, it is very low frequencies. At 400 gigahertz it is too high, so of course, like GSM, we have two bandwidths, 900 approximately 900 megahertz and 1.8 gigahertz, DVB-T and other services working in other. So radar working, how I already mentioned, it in bandwidths S, L, C or X. We are focusing now on C and X. If I will continue, there is some utilization models. So the utilization models is divided to 3 different brands. It is individual licensing. So it is individual licensing. You get license for specific band for user station specific assignments, often with coordinates. So it is geolocation for some. What is important, you need to fulfill EIRP, so it is isotropic radiation power. So it does not mean that you get permission for some specific bandwidth, but of course there will be limitation in your emission power, because it is difference if we will use transmitter 1 kilowatt or 1 megawatts, of course, because if we will use higher power, of course your range will be much higher, so you need to be careful about this. So it does not mean that you get permission or you paid for permission, use some bandwidth. There is limitation, of course, in power. There is more limitation, but it is limitation in power, antenna pattern, emission mask, and so on. Then is group shared licensing. It is like national PPDR. It is public protection and disaster relief. Imagine if will be some earthquake or something like this. Of course, like government needs some radio frequency that will be, in this case of some disaster, available almost everywhere and will be free for this emergency cases. And last one is general license exempt. It is strictly limited to SRDs. It is short range devices, and it is mean like Bluetooth or something like this. There you don't need, it is strictly limited to some really short distances. So it is like general license exempt, so you can use it almost anywhere. Of course, if we all of us use, I don't know, Wi-Fi in same frequency, there will be some influence, but honestly, who cares? It is our problem, if I can say. So, but it is some, I don't know, Bluetooth, it is some other similar services like this one. Okay, then transmission regulation could be channel based. So in some specific frequency bandwidth, you get only, like example, 1 channel permission, 2 channel, 3 channel, something like this. So it is depends on your service, of course. So you will get fixed channel and you can use it just this channel in this bandwidth. Then it is regional based and it is geographic restriction. Okay, you can use in Assam, you can use in Delhi, you can use in Mumbai, and so on, because there is not influence between these things. Then is point-to-point, like licensing, and it is depends on site coordinates, azimuth, and again radiated power. What is mean? I don't know if it's in Czech we have like example coverage by high-speed internet with some point-to-point access, because if you have some small village, some small village that is not close to any city and you need high-speed internet, there will be some like access point from from city to this village with line of sight, and you can use it just in direct azimuth transmission in specific power and only between these 2 points. It is useful because it is not easy. I need to move. Oh, but I am connected? Yeah, I am connected. Oh, yesterday I checked it and working. Maybe some connection issue only. But yesterday working fine. I'm sorry about it. So and then this one. Yeah, I have it connected Wi-Fi, unfortunately, to Eduram. Oh, you don't see it. I see it on my second screen. So it is okay. And just before 1 minute, I sent you email with tutorial, so my Wi-Fi is okay. Okay. I have downloaded manually. I expect maybe some problem. So I will show you your allocation table of your country. How look it. Just give me a sec. So it is national frequency. Okay, it is national frequency allocation plan. It is from 2022, and there you can check wall allocation that is available in your country. So I will go down. So you can see there is division to some region. You are in region 3, and this is some general things. Okay, and now you can see this allocation table. So we will go to first number. It is always frequency band. It is like primary and secondary usage, how I already explained. It is a huge document, of course, because it is true, and it is very often updated, so you can check it later. It is 1.6, 1.8. We go for some interesting frequencies for us. 4 gigahertz. Okay, radio location about 5 gigahertz. You can see, and so on and so. So it is, I don't want to say boring table, but you can see everything where is everywhere. So it is just this PDF. You can download it from a link that I provide. I don't know why today not working, yesterday working. I already checked everything. But if you want, I can send you this document also, so you can already check it. And also, please, in tutorial you will have there links and citations, so you can easily find it also, this document. It is publicly available, of course. And there is in X-band example of, you can see radio location, radio navigation. So it is our radars in X-band. So it is just from 9.3 to 10 gigahertz example. And it is for each region and for India specifically. So you can check it easily. So there is like summation why we can just show up and measure wind turbine echoes, because we need right band, on which depends right band, of course, on our devices, on our radar or software-defined radio and so on. I don't know if you have experience with SDR, but we usually use some SDR from National Instruments, and I will show you someone. It is devices like these devices, 1 kilo maybe, and it is really powerful. It has transmitter, receiver, multi-channel, and so on. It is also relatively expensive, but if you compare with price of radar, it is very cheap. I think that this, of course, they have multiple models, but price vary about 8 up to 12,000 euros or something like this. But still, if you compare with millions for radar system, it is still relatively cheap. Then you need, except right band, of course, license and authorization, regulatory site clearance. So it is site approval. Okay, you get transmission that you can transmit, but you need site approval. Okay, you can go to this exact place with permission, and from this place I can start measuring for installing this radar station or for measurement. Of course, if it will be classic radar, you need a lot of more document than if it's just temporary one-time measurement. It is much easier. But before you go to these authorities, you need prepare complete documentation of your setup. It is clear because they need to know what you will transmit, which signal, which power, emission limits, duty cycle. It is also important because we make measurement in pulse regime. So it is duty cycle is 10%, 5%, 90%, continuous. Do you understand me? And also it could be possible time or geography restriction. Imagine if you, what is possible time restriction? During daytime, maybe somebody use frequency somebody else. So you can't use the transmission during daytime, only during nighttime or something like this. And geography restriction, it is clear, it is with geography where you is your location. So all this you need to fulfill before you go to make a measurement. And I think that get permission is not easy task. It could take a month of work. So, there is step by step what you need to do. Choose band consistent with your measurement goal. So you look first to document. Apply to WPC for temporary or experimental license. You need to tell them center frequency, so it is your carrier frequency, peak, mean, radiation power, antenna gain pattern, geographic area, where you want to measure, and schedule when. And you probably fill some form, prepare some document, and put to authorities and wait for answer. Then you obtain from SECFA, it is Indian like authorities that give you this clearance, sitting clearance for any fixed site, and adhere to aviation high keep out rules. Also, you need to protect primary users in case that somebody uses this frequency. Like 2.7 to 3, it is protect aeronautical radio navigation or radio location. In 5.6, it is for weather radars usually, and 9.3, 9.5, it is maritime meteorological aids use, and so on and so on. So you can see it is exactly our frequencies that we are using. It is good to use same frequencies like your radar. Why? Because your measurement will be exactly valid and will be same reflection on same frequencies like measures your radar. So we use it, this national instrument SDR, and it is in S-band about 3 gigahertz, how you can see later, I think tomorrow. So if you confirm spurious out of band EMC limit in the license, duty cycle, and so on, you get clearance and you can go make a measurement. Only there will be some exception if it will be close to national border or some special areas, of course military. There maybe will be much more difficult to get it. And unfortunately, big wind turbines farm, it is somehow protected area, but you understand me, because it could be if somebody destroy it like terroristic attack something, it could destroy power in the whole area or something like this and cause it a lot of problems. But we not be pessimistic that we are close to national border and we are inside country and not will be so bad. Okay, there one quick repetition about radar signals and we will move to MATLAB. So it is our transmitted signal, it is PRI of all this, it is pulse repetition interval, then is next pulse repetition interval, and we are pulse transmission, and go, and we continue. Then we have CPI, coherent processing interval. It is this called slow time, and you know why? Because we need compute spectrum. So we are sending multiple PRI, like one example 1000, and then we in slow time compute spectra, which is in, how to say, 1000 frequency line, because we have 1000 samples. It is like this. So what is important, it is blind zone. So just for repetition, blind zone is a zone where I can't receive any signal because I will destroy my receiver. Because reflection in case of target will be so high that will destroy. Because receiver must be extremely high sensitivity, because he detecting so small attenuated signal that must be very sensitive. Then we have instrumented range. So it is, how I can call it, listen time, when our receiver listen if he gets some answer or no answer, and it is mean no target, and it is just noise answer, or reflection from environment. It is always reflection from environment. And we use it words clutter. It is special words that is used for reflection from environment, clutter, C-L-U-T-T-E-R, clutter. Because this word has also another meaning, so it is little unusual. Then we have dead zone, and dead zone we use it for changing to another pulse regime, or for diagnostic of our radar, and so on and so on. Everything what you can imagine. So we are receiving only in this, not small part, in this part, reception period. So now there is typical example. By the way, these values are from our measurement, from real measurement. So we use SDR NIX310. It is about this 10,000–12,000 euros devices. I will show you all details, what is structure of this, what is block scheme, but later when we designing measurement chain. And what is parameters of our measurement? Carrier frequency was 3 gigahertz. So wavelength is 3 centimeters. Pulse width is about 200 nanoseconds. PRF, it is 2 kilohertz, so inverse value is PRI in time. Sampling frequency is 40 megahertz, because everything what I show you there is continuous. But of course, remember, after I receive analog signal, first thing is AD conversion. We are working with samples. But if I will draw this picture like in discrete time, it will be more confusing. So we are all picture using in continuous time, but we are working with samples. Still, you need to have this information in your mind. Where is my mouse? Okay, this. Then duty cycle. So if you see that pulse width is 200 nanosecond, it is this one. PRF is 2 kilohertz, so my duty cycle is only 4%. So only 4% I'm transmitting, and about 90% I receiving echoes. And last 6% it is this dead zone, or 10% it is depend. Recovery time we set to 0, and guard interval is 0. What is this? I can say easily that is some time for recovery and guard interval, protection of my receiver, and so on. But we can include everything for simplification to dead zone. Or you can see this one, this blind zone, it is not exactly at to end. So it is some guarding interval, something. So, but let's put it to that zone, everything. I just want to show you that there is more deep, some recovery time guard intervals, but you can see I set to 0 because I don't care about them now. So what will be blind zone? So minimum range where I can detect target. For me, based on this parameter, it is only 30 meters. Oh, it is not so bad because from okay, from 40 meter, 50 meter, I can easily receive reflection for target, but not until 30 meters. What is maximum unambiguous range? So it is only limitation of pulse repetition frequency, and it is speed of light divided PRF. It is approximately 75 kilometers. Don't expect that will be 75 kilometers. No way. It will be 10 kilometers. It is depends on your power also. You remember, it is this is just theoretical. So 75 kilometers. So it is clear that after that I can measure only between 30 meters up to relatively 75 kilometers. Far, it is too far, and close, it is too much close. It is in 2 mile zone. So what is instrumented range? It is listen time. It is listen time, this one, and it is PRI minus tau plus T res, and but this is and guard interval, but this is 0, so it is about this almost 500 microseconds. So it is 4.9 kilometers, something example. So it is clear that is almost like unambiguity range, because this 30 meters, it is not so big limitation, but it is in theory. So we of course make sample to range spacing. So we have several digital samples in one theoretical resolution cell. If you have resolution cell, it does not mean that in this cell is one sample. There is multiple sample. I need more information, not only one value about one sample. It will be constant. It is not almost any information. So there is more samples, and how is fit with my calculation? So range resolution we already calculated of uncompressed pulse. It is depends on tau. It is length of my pulse, and it is about I don't know. I even don't move any cable. I will try. No, I tried. We are back. There. So we have several digital samples within one theoretical range resolution cell. This does not change the physical resolution. It is just more multiple samples in one resolution cell. So this physical resolution is set only by bandwidth of pulse. So be careful about this. Not by length of pulse, by bandwidth. We yesterday derivated these things. So what is sample range spacing? My sampling rate of this continuous signal that I receive is 40 megahertz. So delta R of sample is C divided to F, so it is about 3.7 meter per sample. So you can see my resolution is 30 meters, but this is about 3.7 meter per sample. So it is mean approximately I will have 7 samples per 1 resolution cell, something like this. So unambiguous radial velocity, okay, we can also compute is 50 meters per second. And now my question will be, what do you think with this? If we will have target and 3.5 kilometers, are we inside instrument and unambiguous range from point of view samples and all setting? We are in the right way. Can we start measurement, theoretical measurement, because of course there is still not power. So we will measure what is time delay of target. So it is 3.5 kilometers. So time from transmitter to my target wind turbine and back will be about 20 microseconds. So fast time sample index will be about 801 samples. End of transmission pulse, it is about 8 samples. So if I will get this value minus this value, I get this value. So answer, if we are in range, yes, of course, because it is between 30 meters to 75 kilometers. So is it clear? But with this example, I want to show you how you can easily compute. This is not any magic. It is only few formulas, and you can easily check it. You can even check if you don't like your resolution under 1 cell. Okay, make a higher sampling frequency. Of course, higher sampling frequency is more data, and you need to store somewhere this data. And I must say that your hard drive really fast disappear because it will be full. Because imagine that it is number of sample per second, 40 million, but I don't, resolution of quantization, it will be about 14 bytes. So 40 megahertz multiplication by 14 bytes, it is size of data per 1 second. Honestly, we made about, I don't know, 20-25 measurement, and we have about 8 terabytes of data. And it is only few measurements. And one measurement is about from 8 up to 15 seconds. So we have only 2 rotation of wind turbine, and it is gigabits of data. So, and if you need to pre-process all this data, oh, it is for days, because you understand me, it is not hard computation, but just this data throughput, you need just process all this data. So we always pre-processing all this data, and what I will show you later with our real reflection, it is already pre-processed, because if I will give you raw data, my notebook just will die, because it is not possible to compute. We have some PC station with 128 gigabytes of RAM, big hard drive, about we have like hard drive, how to say, storage that has about 80 terabytes of data, and we can like written speed is about 1 gigabit per second. So even if your SS drive, it is very slow. So there is about 20 SS drive that is connecting in parallel, and the data just flow to this drive. So it is really huge. But I think that is clear, because so you can't make higher resolution with sampling frequency, but be careful. It's your amount of data start be really exponential growing. It is really huge. But in present time, it is not so big problem. You can do it. So now we open first script, and please change, just play with this. I will show you, of course, change PRF change PRI, change pulse width, guard interval, and watch the result. It is best one. Of course, I will show you some settings, but it will be nice if you can play by own. So I will switch. Okay, my eyes is not so good, so I will close. We don't need. So check it. So there is some definition of variables only: speed of light, carrier frequency, wavelength, PRI, inverse value as PRF, length of pulse, recovery time, sample speed, where is target, it is simulation of target, what is echo amplitude, it is also simulation, and everything you can change it and always you get another result. And what is signals to noise ratio, because of course if it will be without noise, what will be answer? Always one line, where is target. So if I will run it, you will see always something like this. So it is my echo, this is noise of course, and this small thing, how you can see, it is blind zoned, because it is only 30 meters, so it is small. But you will see details only first 5 kilometers. But what is full span? Oh, sorry, I don't, okay, it is 75 kilometers. And now in command window, it show you all results, just to be comfortable. So minimal blind zoned, instrumental zoned, sample spacing, target. It is time delay of target. It is T but not tau, but never mind. Which index of sample, and it is all. And you can just run it. You can just please for 2-3 minutes just play it, try change. I don't know, PRI. We can or we can, yeah, pulse repetition interval. We can make 1000. Oh, sorry, check keyboard. 1000. Tau will be only 20. So if it will be shorter, what will happen if we will continue? Target is still in 3 gigahertz, and check. Now, because I change in blind zone, it is not 30 meters, it is only 3 meters theoretically, but unambiguity range, because I change bandwidth, it is 150 kilometers, spacing, and so on and so on. So please just play it, try it, and I will switch and to this, and there is what you can see. So if you increase pulse repetition interval, what's happen? It is clear, it will be instrument range will be longer. So it will increasing my unambiguous range. My radar will see to longer distance theoretically. I think that is clear, and you can play with this. It is like you can also you can change signal to noise ratio. If you are increasing noise, your target will slowly disappear this amplitude, of course, because it will be masking in noise. If you changing guard interval, you can try it. If you increase your guard time, changing pulse width. If you will increase longer pulse, radar resolution becomes worse, of course, and blind zone will become larger. So we can change it. If we will change, where is it now? So it will be not 20 nanoseconds, but I don't know, 500 nanoseconds. You can see it is now 75 meters blind zone, instrument range 150 again, of course, because it is not influenced. So what is important? PRI and tau. length of pulse. And the rest is speed of light, it is still same. Of course you can change it, but it is not so important. You can change it also, we can try like 20, we can put minus 20 dB. Okay, do you see? Almost disappeared. So we know where is it, because I have put line there, but you can't recognize. So it is just easy evaluation and playing with these values. Is it clear, this one? But always check for full range. It does not mean that be careful about 5 kilometers. It is just details, because I need to do it this zoom, because if I will show you always this one, there is nothing visible. Okay, of course you can change also target and amplitude of target, but this is just for example if you are in the right position. Oh yeah, it is under 5 kilometer. It will be at 7 kilometer. Yes?
Sir, I have one question. Sir, one of the crucial thing is sampling rate.
Yeah.
It should be 1/2 divided by pulse width, right?
It is related to bandwidth.
Bandwidth, correct.
Be careful, not length of pulse, because if you use some modulation, then it's not tied with length of pulse. Of course, if will be unmodulated pulse, it is science function. You are right, completely right, because it is just inverse value of length of pulse. But if will be with inner modulation, it is another formula. It is divided to 2b. It is just strictly to bandwidth of this inner modulation, not length of pulse. Be careful about it.
My question was that if we do that calculation, that optimal sampling rate should be 10 megahertz, but you have chosen 40 megahertz.
Yeah, because of course.
This will increase the data output.
Yeah. Because you know. Usually we like oversampling little, 2 times, 3 times, 4 times, because always I make, if I want to process, I can always do it decimation if I don't need. But why we use it higher frequency sampling? Because in case that I need it and I don't have it, I need go make again measurement. And I don't want go to measurement if it's 150 kilometers far away from me. So we push frequency sampling rate to maximal limit what we can, because always you can make decimation if you don't need. But if you make like minimum sampling rate, just fulfill sampling theorem. And in case that you need higher, you need go to again outside to make measurement.
So what is the general rule of thumb?
Right. How many times should we take extra sampling? Like 1 time, 2 time, 3 time. 2 time is the theoretical limit. So
yeah, it is a hard question. Honestly.
Okay, sir, no problem. I'm just asking
it is
because
hard question. I don't think that there is any rule of thumb.
There is no rule of thumb.
No. I don't know. We just try push it through. Okay, we use it 1 gigabits LAN, because it was connected not of course to USB, because it is 1 or 10 gigabits LAN network. So with okay. So we try to push to maximal, almost to maximal sampling rates.
Okay, no problem.
So if you make more and more sampling, it is not harmful to anything. Okay, if you will make extremely large sampling, really 10 times, 20 times, then can be some dependency between sampling of noise, some correlation thing, but I think that you don't have chance to do it because you don't have so quick device to make so quick sampling. So we use it about 3-4 times more,
Okay.
but there is not any rule. Sorry.
Okay, sir. Okay.
It is bad answer, but
Yeah, no, it is okay, sir. Okay.
okay. So we will go for another tutorial, and we go for range measurement accuracy. You see this similar slide yesterday, but
Okay.
I just think during evening about it, and I just want to give you some more explanation because there could be a little confusion, because this is since function, and you know that since function is, if I have rectangular pulse, it is spectrum. But be careful, this is since function, it is true. But it is cross correlation, there is time, it is not spectrum. It is little confusion why. I will just explain you. So I just during evening adopted this slide because I don't want that you think that this is spectrum of the rectangular pulse. It is not true. And why? If I will have rectangular pulse, just rectangular pulse, my cross correlation is triangle, clear. Spectrum will be since function, clear. But now I don't use rectangular pulse, but I use LFM pulse, linear frequency modulated pulse. And definition of this pulse in time is this one. It is exponential jpkt squared for time duration of pulse. If you make visualization of instantaneous frequency, it will be linear increasing of frequency. Zero otherwise. So it is definition of this pulse. Received signal is transmitted signal that will be attenuated and delayed. Do you agree? Attenuation and delayed. Clear. Impulse response to my LFM pulse due to cross correlation will be complex conjugate minus t. So how it looks like? It will looks like this one. So it will be impulse response for cross correlation. So I will compute received pulse with impulse response, and you get this function that is since function also. And why? Because if you will see spectrum of LFM pulse for, how to say, enough large bandwidth, not for extremely short bandwidth, for some kind of bandwidth, it will look in spectrum like pulse, but in spectrum. And if you make inverse Fourier transform, and in spectrum we have rectangular pulse, almost rectangular pulse, what we get in time domain? It is symmetry of Fourier transform. We get since function. So since function in time. Do you understand me? In time, if we have rectangular pulse, spectrum is since function. And due to symmetry, if since function will be in time, in spectrum we get rectangular pulse. So it is I don't know how you call it, this property of Fourier transform. Symmetry, duality. Okay. We call it symmetry or duality, so there is little confusion about words, but so we are in time. And it is time, and this you can see it is again cross correlation. This is cross correlation of rectangular pulse, and this is cross correlation of LFM pulse. So it is in time. I just won't make this explanation because I just really during evening. I hope that don't think that it's spectrum of rectangular pulse. No, we are in time domain. It is just for explanation. So you will see there I think that is clear because Fourier transform is very well known everywhere. So, and filtration also. So I just want to present you this one. Okay. So and okay. Last thing. What you see there? It is not in zero. Maximum is not zero. Y is in tau d. It is our time delay, cross correlation. And from position of maxima, I can recognize, oh yeah, there is my time delay, and I can convert it to distance, and I know where is slant range of my target. And this is LFM compression. Then we have NLFM compression. Then we have so many different Barker codes, and so on and so on. Phase coding. In the last slide of this tutorial, I have again application where it's about 5 different pulses, and you just can click and present results of this. So it is just explanation that that is not spectrum all. Maybe it was clear from yesterday, but I was not sure. So about range resolution capability. I already present you this picture, and you know if I have this since function, and if I can distinguish both maxima, perfect, good resolution, enough. But now I will show you that it's not so easy. In radar, is anything not so easy. There is always some complication. So, imagine, matched filter impulse response is essentially time reverse conjugate of transmit pulse. Do you agree? We just show it in previous slide. So, when we have 2 targets, we have 2 time delays. Clear. And how will looks matched filter output? This, this one, if we have 2 targets. Of course, it will be coherent sum of 2 shifted impulse responses, something like this. But it is complex. It is not real. So it is complex amplitude. So one complex amplitude, second complex amplitude. And when it's complex, it not is only amplitude, but also phase. And sum of phase, so what will be results of this summation? It is depends not only on both amplitudes of targets, but also on different phase of this both complex amplitudes. And imagine, if phase will be 0, then it will summation, it will be undistinguishable. If it will be 180, it will be 2 different main lobes. And how you can recognize which phase will be? It is random variable. It is depends on target or movement when you get reflection. So it is not depends only amplitudes of reflection, but also on difference phase between of these 2 targets, because it is complex amplitude. So if we assume the 2 targets are at different position, corresponding 2 delays with relative phase, we will ignore noise now. The difference between one complex amplitude and second will be delta phi. It is difference phase. So you can see it is one complex amplitude, second, and this is this difference phase. Of course, you can use phase 1, phase 2 and make differences, but I think that is better if I use just delta phi like difference phase. So even if this amplitude will be 1, this will be 1 different tau 1, tau 2, and you can say, yeah, I can recognize, why not? No. Unfortunately, it is depends also on phases. So in some case, yes, you can easily recognize. In some case, no, you can't recognize because it will be summed together because it is depends on phase. So if our phase will be 180, it is strong destructive interference between the lobes, and it will be deep valley between this one and we don't have issue. And if will be phase 0, it is constructive interference, and you will see one main lobe. So it is not depends only on time delays. Of course, if will be time delay higher, you can recognize, and phase dependency not will be so high, because I don't care, it is so indifferent time delays. But if time delays will be closer, then this random phase start be important, and it is random, it is the worst. Sometimes you can hit good, sometimes you can hit bad. Okay, so open range resolution application. I will close this one. Okay, this one. This range resolution application, I still updating this application, and now didn't work only with rectangular pulse, but also with linear frequency modulated pulse, non-linear frequency modulated pulse, and Barker. And you could set a lot of parameters and always watch results. So I hope that will work for you. I tested all application and works for me. Okay, it is works, but it is in my site. I am glad that you have this screen there, because I don't need to do it this one. Okay, just run it if works for you. Check. There is controls, so you can easily. I will do it this one. I can't make to full screen because I don't see some border, so it is just there. You will see always pulse autocorrelation function. Maybe I can limit until -40 because it will be more detailed, but it is not important. You can see this is first side lobe, so it is if I put a rectangular autocorrelation function, it is triangle, but it is in dB, so it is not triangle because there is, of course, not linearity, but it is triangle. And check, if I have two targets, there delta R is 60 meter, so it is mean it is first target R1, where is location of first target, and this is difference between targets, if you get my point. Okay, I can put R1, R2, but I just do it the difference between targets because it is better. And recommendation, visible, if you can see, the resolution is about, for rectangular pulse, about 6 kilometers, so of course you can't recognize two targets, not any change. If I use LFM, resolve it, yes. Visible 70 meters, and you can see, but it is hardly visible. You can see this is only what will be about 4 or 5 dB. It is not big difference. We are on the edge. And there you can then change LFM, non-linear frequency modulation. You can see there is bigger differences. There Barker. Barker in this case didn't work, but Barker has another advantages. I need to set up another parameters for this. So generally in waveform you can see this for waveform. By the way, it is modular. So if you want to put another waveform, just to put it, you can program it and put it, so it is modular. And there you have second option is scenario. Rectangular pulse, low resolution, LFM, two equal targets, weak target in side lobe, sampling effect, and comparison LFM and LFM. So it is like presets for individual scenario. It is just what I think that could be useful for you. So you can see now I have one target 3 kilometer. Difference between target is about 6 kilometer. So I can recognize both target, but it is 6 kilometer differences between targets. LFM. Oh, there I have some. Okay. And there is visibility presets. So you always change scenario and visibility preset. If visible, non-visible, of course you can change it manually. But sometimes it's hard. It is a lot of parameters. So there is some hint for you how to use it. So check pulse length, sampling period, bandwidth is still same, and now it's visible. So it is visible about 70 meters. Will be visible. It is mean that will be 70 meters far away each other. Hardly visible 30 meter, and invisible until 11 meter. It is just. It is not exact value. It is just some presets that I want to present you, show you what you get. So is it clear? Two targets. Resolution 67.5, and you can see. And there you can see the phase change. So we will put 0. Did you see how changing just phase, nothing else? So 0, it is the worst case, and I can still resolve. But if I will dial hardly visible, this is almost not possible to resolve. Due to noise, if will be there noise, forget. One main low with noise, no change. And check if I will put 90 degree. Do you see? Just phase, nothing else. And phase is random variable, so 180, it will be best option. Yes, it is. It is completely valid with my theory that I present you. If we put 0, no change. And if we, this is distance between targets, it will be 40 meters. Okay, one main lobe, no change. There is not two targets. Weak target in side lobes. What this mean? Okay, not Barker. We will put. Okay, we will. Okay, I know why is Barker. What this mean? Main target, big ship, big aircraft, and then some really small aircraft. For acrobacy, something really small one. The amplitude is small. And what's happened? Sometimes strong target could mask your weak target. So in case that I will changing value and will go close and close, this slope will continuously will be masked this main lobe. So we will try it. And now is difference between targets 500 meters. So we will put 400. You can see it is closer. Okay, I will speed up. 300, 250. Okay, done. Two targets, but only one is visible because second one is that one. And always, if you make some mistakes and put some parameters and you won't go to back, just use these presets, visible, invisible, because sometimes it's handy. Next one is sampling effect, 10 megahertz. Very, very hardly visible. If I will put visible, Okay, where what's do it if I changing sampling? What's happened? Everything is like in finer resolution. If you, because okay, I will put it to 5. Remember, this is just visualization of spectra. Now I put 5 megahertz. Okay, you can recognize, but you understand me. It is not nice spectrum. It is not to sinus function. Okay, you can maybe hardly recognize that will be sinus function, but you need to have a lot of experience. So then still sinus function hardly visible. 20. Okay, we can discuss it. Maybe 30 better, and 40. Okay, I know how I answer you now. It is just about resolution. If you don't need, if you want nice result, use higher sampling rate. If don't want and you don't need.
Sir, my question was, I understand this point, but I'm just saying, is there a rule of thumb, right?
Yeah, I get you, but I still don't know answer about this rule, so I don't know. I just thinking about our measurement.
Because there are a lot of systems, like when we are doing signal processing for military, they have a very tight requirement. So they want to keep the sample rate as minimum as possible.
Yeah.
Speed up everything.
Okay, I get your answer now. But you are in commercial zone, and you know why? It is just about money. Because it is about AD conversion. And military system always almost need work in real time.
Yes.
The lowest sampling rate. Because if it will be higher, you can't process in real time, or your AD converter will be so expensive that nobody buy it. Okay, so it is, oh, you don't tell me first time that is commercial, so it is clear, it is just about money. And stability, and the important is that it's in real time. And of course, it is different if you want to process 40 million samples per second or 20 million samples per second. It will be about real-time processing. Of course, it is depends on your device. I don't know, but I'm pretty sure that will be only combination money and real-time processing. But I must say that never you can go, okay, lowers the possible, but I suppose that never go to limit, like
Obviously, limit obviously 2-3 times more than
it is very dangerous, goes to limit, because I suppose, okay, tell me, in your devices, you go to 1.5 multiplication of minimal sampling rate 2 times, or what?
So first of all, I don't have access to any devices, but what I'm planning to do, that whatever I'm doing calculation with, that should be usable for actual device.
Okay.
Actual device, their requirement is they need real-time processing.
Okay, one more answer that is good, I think. Now we are working in MATLAB, so I can put any value. But in reality, I need found AD conversion that fulfill my requirements. So please take. No, it's okay. It is just my laptop's off screen. It is just about it. So it will be okay. You will plan experiment.
Sir, my question is answered.
Yeah. Oh, thank you. So is it clear? Can we continue from this application? Please play it during night. Maybe if you have question tomorrow, I will answer you during tea break or something. I didn't find a mistake in this, so I hope that will work for you. Maybe you will find some mistake. Sorry? Tea break. Okay, so tea break. Okay, we need to really speed up. It is too in detail. Never mind. Okay, so tea break. Can we make tea break only 15 minutes, not 30 minutes? So 15 minutes, please. Because 2 more lecture waiting. And only 2 applications. So we will continue. Range resolution capability application I already show you. There is some text description for individual scenarios, so you can check it later. And we go for range ambiguity and resolution. You already know what is range ambiguity when we receiving these pools and we don't know, okay, it is right distance, but our radar tells us, okay, it is this distance. So we know it. Then exists, so call it staggering, that we changing sending time of PRI, and from this inequality we can get right answer. I will continue. And how we can do it? There is just base formula that I show you yesterday, and now I have one real example how is processed. So imagine we have PRI 1 millisecond. Real target is in 210 kilometers. So now it is non-staggered PRI, so it is mean it will be constant bad value of distance, of range. So we will continue all these values. I think that we will do it together, but we need to save the time, so I will show you result. If we will continue, you can see that the time delay, true time delay is 1.4 milliseconds. Unambiguous range is about 150 kilometers. So we are outside. So is it clear that second pulse already is transmitted before we receive echoes from first target from first pulse? So, okay, 150. And what we are measured by radar, we measure T true. Of course, we know it in advance, but generally you don't know. Modulation PRI, modulation 1, and results is 0.4, not 1.4 milliseconds, but 0.4. And if you could recompute, so measurement range is 60 kilometers. You remember it was yesterday example. So if it will be static target with any PRI, you will see 60, 60, 60, 60, 60, 60, and you think that is static target in 60 kilometers, but it is not true. He is in 210. So now we have completely the same target, but PRI we have two. 1 millisecond, it was previous case, but second will be 1.2. So it is mean first 1 millisecond, second 1.2 millisecond, and it is just changing like 1 millisecond, 1.2, 1 millisecond, 1.2, and so on. So first, now we have two unambiguity range. Why? Because from first pulse and second pulse, I think that is clear. So first is 150, it is same, of course, and second is 180. What is measured target range by primary radar system? First, okay, 60 kilometers, it is wrong. Second, it is again modulation, but by second pulse, so it will be another modulation only. 30 kilometers, not modulation, modulo. 30 kilometers. So I have now two results, 60, 30, 60, 30, 60, 30. Both wrong, I know. But how I can from these two bad values correct value. It is by how to find exact right value range. So the true range must satisfy this condition. It is first measure value, but second measure value. So it was 60 and 30 or what? Yeah, 60 and 30. Modulo iambic is 2. So we can compute from this true range. From this one, but we have problem. What is t? We don't know t. This is no problem, this is no problem, but t we don't know it. But we know that second condition, yeah, this is the second condition, sorry. So stagger computation, and now how we satisfy this one. It is this one is greatest common divisor. You know. So from 150 and 180, the greatest common divisor is 30. So if I will use this equation divided 30, the result will be this, and the result will be this. So real target resolution is measurement plus t. It is the original equation, but t is 1. So 60 plus 1 multiplied 150. Win-win situation, 210. So you can see how staggering helped me resolve this ambiguity range resolution. So you can see. It is easy, but I want to put this example because you can easily follow. This is example how looks in real, because I always show you first PRI, first pulse reflection, first pulse reflection, first pulse reflection, and you can see that this is 210. But radar told me 60. But in reality, you don't see this one by one, but you always see this one only one time. So I will send and second send and receive, but from first one. It is from second one, and so on and so on. It is always mixed. Understand me? So it is ambiguity. There is script that show you just this picture, but again it is variable, so you can change this position, target, position, answer, response, and so on and so on. So you can play it with this parameter, but now I think that is not necessary because it is just about visualization. Second is staggered, so 1 millisecond, 1.2 millisecond, 1 millisecond, 1.2, 1 millisecond. You can't recognize, of course, because it is very similar value. And you will receive this one. Check. First, answer. Second, but second another answer. And now you can see that this size and this size always is different. There was constant. So it is these two our values. And from this I can solve the equation that I already show you. So it is this one. There you have name of script, so you can try it, play with it if you want. And there is example how works in a real. I make just some GIF, yeah. Because this is produced by this script, but due to that, if you want to run it, you can easily without any problem, but it is very slow because it is due to generation of this GIF. So I don't want to run it because it takes 1 minute or something like this because it is very slow. But you can see what you see like on radar range 60 kilometers, still constant. but bad. There you see 60, 30, 60, 30, 60, 30. It is due to different PRIs, 1 and 1.2 milliseconds. It is also bad, but we can solve. Oh, thank you very much. Okay, can I continue? Again, you could just run it. You have scripts, so just use it. And there is a last script, for example, staggered or non-staggered. It made all calculation of this equation automatically. So you can just run it script, change value, and you will see results. So you don't need to compute manually and solve this solution. And always is presented just this picture. So on this screen you will see non-staggered version. There you will see staggered version. And there is a reconstruction of numbers. So you can see one value, second value, one value, second value, and so on. And where meet each other together, it is our solution of our equation. It is 210 kilometers, you can see this one. So easily just change target distance, I don't know, to 250. You can change position of staggered PRI, like 1 millisecond, 1.3, 1.4, and everything will be recomputed. So you will see true delay, it is exactly right value. You will see what is module measurement delays and correspond distance, and how is solving solution and what is result. So it is like this. It is 3 scripts, 2 for visualization, 1 for computation. And you could put almost any values. Of course, you need to be careful and not put, if this is 1 millisecond, this 1.1, so you can't put that this will be 1 second or something like this. You need to put some reasonable values, because I don't put to this script some boundary condition or something like this. So be careful, but for normal real values working fine. There we will talk about radial velocity measurement. You already know that is very, very similar to ambiguity measurement of range. Again, we need to solve this blind speed. Blind speeds mean that target with blind speed, this one, where k is integer number, 1, 2, 3, 4, 5. It is multiplication. K multiplied by c divided 2, it is constant because it is speed of lights. PRF, pulse repetition frequency, and carrier frequency. So why I care about blind speed? Because radial component varies from Doppler frequency. Doppler frequency is min fc to r divided c. So we evaluate the subsequent received pulses phase. Phase is derivation of frequency, and from frequency we could derivate, of course, speed. So why, and last thing, why there is n? Because I can have it multiple pulses in one CPI, coherent processing interval. It is just about this one. So this is signal model. It is example of signal model. So imagine that you receive from Doppler phase across pulses. You unwrap phase over CPI or use FFT. There is 2 approaches. So imagine you will get 1 sample, second sample, and you will evaluate what is difference between phases. between two samples. Then between second sample, third sample, fourth sample, five sample, and continue and continue and continue. And what is unambiguous Doppler or blind speed, because it is the same almost. It is mean sampling at PRF. Do you Do you remember slide with fast and slow time? It is this one. So, maximal Doppler depends on pulse repetition frequency divided 2. And Doppler must be lower than this value. If will be higher, we have ambiguity speed. So, if I will recompute, I can maximal speed will be lambda multiplied with PRF divided 4, and blind speed will be m, this one, where m is integer because I always receive same value. It is just multiplication of. So if fd is equal to m multiplied by PRF, df is 0, and we can indestructible. Do you remember from last lecture this picture about wavelengths? That we have motion, but phase always due to sample was 0, so we see constant. It was static target. So it is this case. So what is Doppler resolution over a CPI? It depends how many pulses in CPI. 1000, so it is this matrix. I have 1000 samples, and in each corresponding sample in CPI I compute spectrum. It is second approach. It could be computed from derivation of phase or from spectrum. If will be from derivation of phase, you expect when you use unwrapping of phase that will be linear. And if not will be linear, then is something wrong, and there is some blind speed or something like you are outside of control. Or you can do it from FFT. And if you do it from spectrum, what we are looking for? Maximum amplitude in spectrum. And it will be your Doppler shift, and Doppler shift is speed. It is almost the same. So there is two approaches. My scripts again use it both approaches. So you will see computation from phase or from FFT. They produce little different results because it is different approaches. So we will see. So if I have signal model across pulses, I will get this. It is my signal, amplitude, exponential j phi 0. It is some initial phase plus 2p fd. It is this Doppler shift, and tk is sampling rate. It is some in some specific time, plus noise, white noise. So phase increase linearly with time. So we get this one. Phase difference sequence will be always wrapped to minus p to p. Why? What is complex exponential? Unit circle, if you remember. Because Euler equation, it is complex exponential is cosinus omega t plus j sinus omega t. It is unit circle. So we working, of course, always with this one. So if you are computing FFT, it is clear how we look spectrum of discrete signals. It is spectrum that is repeated, always repetition, because it is periodic spectrum. Why is spectrum periodic? Due to complex exponential. You are always in same circle. And what is this repetition of circle? It is this periodicity. It is still same. But I suppose that a lot of teachers already told you this one. So now there is example, and again we will see application. We have carrier frequency, pulse repetition frequency, PRI is 125 microseconds, PRF is 8 kilohertz. We have n pulses. So what is mean? It is length of CPI, because I have PRI, 64 pulses, and from this I will get length of CPI. So what this mean? It is resolution of my spectrum, 64 values in spectra. Why? Because I have 64 pulses. If I will have 128, I will have 128 pulses, and so on and so on. So what is unambiguous range? It is about 19 kilometers. What is unambiguous velocity for this one values? About 60 meters per second. So any speed that will be higher than 60 meters per second will be wrapped to base range. So will show me bad speed. It is same like ambiguity range, ambiguity speed, but we don't say ambiguity speed, but we call it blind speed. It is similar. So Doppler resolution will be about 2 meters per second, because it is depends on length of CPI, of course. So please run it. I will just close it. Range. Okay, I will close it this one. So now I will show you first single PRF and dual, so it is mean in burst. So carrier frequency 10, PRF1 8 kilohertz, 64 bursts, and so on. True speed is 150, initial range it is 10 kilometer, and signal to noise ratio is 20, so noise is very small, how we already discussed it, and it is done. So there you can always see results and check. Single PRF, it is wavelength 3 centimeters, true wire 150. Speed computed by phase is 30 meter per second, and by FFT is 30 per second. Yeah. It is almost same. It is, of course, it is computation, so there you have some finite arithmetics, and there could be some differences, but it is just MATLAB. But check this one. It is not right. Okay, how to do it now? Because I need to check. Just we will put so. Maximum speed that will be recognized well is 60 meter per second, but I put 150, so it show me 30 meter per second, much lower speed, so it did not work. So just put there, I don't know, 35, 30 something, what is lower than this 60. So if we will put 45, 45, you can see I am inside the region of an yes, there 45, and check the slow time phase. It is linear. It is without any problem, anything. Do you see? So maximal recognition speed is 60 meter per second. My speed is 45. Identification of speed 45. Works.
So Vmax depend on which parameter? Like,
No. Now I just want to show you when is good results and bad results produced. It is just default parameters, this one, and I just changing true speed of my target. So if based on these parameters its maximum recognized speed is 60 meter per second, and if I will put 20, like example, it show me 20. If I will put, I don't know, 50, it show me 50. If I will put 59, it show me 59. But you can see we are just on the edge. And if I will put 65, I'm outside. It show me minus 55. So it is mean, what is mean minus? The target travel just not incoming to me but ongoing. If I will put, I don't know, 149, you can see completely bad definition. So what we can this is just presentation of ambiguity speed. So I will put 2, like 55, so it will works. Now I will show you influence of PRI. So now we have, it was single per F. Now we have double. So what does mean? 2 PRI. Because how we can solve this ambiguity? 2 PRI, 1 millisecond, 1.21, 1.2, again, it is very similar. So I will switch to 2 and check. 1 is 8, second is 7.5, identified first place is 55, second, give me a second. Give me a second. Oh, the alias search. No, this works. Oh, give me a second. Yeah, through. Yeah, this works. 55. I am blind. Sorry. So now. Works. If I will put 150 and I will be outside of my maximum speed, you can see that first give me wrong value about 30 meters per second, second give me about 38 or something like this, yes, 38 and 30 meters per second. So both are wrong, but solving same equation but for the speed, the aliased is 150. You can see it is work like with range ambiguity, completely same. And there is this is like slow time phase. It is difference between phase changing linearly. There, what is mean this the alias surge? It is mean range where should be my good speed. Why I need to put this one? Because ambiguity is multiplication by integer, if you understand me. I need to know to range, but imagine we have in range 300 meters per second, so it is, you can put it 500 meters per second, so on, so it is not important. I can change also length of CPI. If I will put higher value, what's happened? Main lobe of first and second is narrow. Why? Because it is longer time and inverse value. It is. So if I will put, I don't know, 200, two ambiguities, look. First, PRI show me that speed is minus 40, second that is minus 25. After dealiasing, we get right value 200. So it is work. It is exactly same like for range, only it is solving ambiguity for speed. And give me a second, I will switch again to and there I already prepare about 20 of scenario that you can test it. Scenario A's, about 10 of them, it is same carrier frequency, single pair F, mode off, same length of CPI, same SNR, but changing just speed. So if speed will be 0, static target, you will see main lobe in 0. If will be plus 42, due to fact that we have maximal recognition speed 60, it will show you peak on 32. Okay, we don't have any problem, everything works. If I will put minus 35, it is okay. It is just mean a negative sign that target goes away from me and not close to me. It is plus minus, so it is clear. If I will put plus 60, I am in maximum speed. It will works, but problem if you put 61 or something, it is just on the edge. If you put 120, it is 60, imagine, it will work for 60 because we are just on the edge. If I will put 120 speed, it will be completely same. Why? It is multiplication by integer, it is blind speed. If I will put 180, same result. 240, 300, 360 and so on, it will be same. Because this mean it is on edge, this will mean blind speed for m equal 1, 180 blind speed for m equal 2, 240 blind speed for m equal 3, and so on to infinity. If I will put 119, it will be same like if I will put 59. It is the same. And if I will put 150, okay, I am out and it show me some bad speed, I think 30 meters per second or something like this. So it is all these scenarios. Then we have scenarios B. There you will changing PRF. So PRF you will stay same and just change PRF. It will show you that just you can change it 1 or second and solving will be always. So that is not only for some specific exact value you can changing this one. So only what is will first alias will be 30 milliseconds, seconds 37 point, and if you will see this one, it will be same solving but just for another values of PRF1 or PRF2. Then we have C, and it is influence of number of pulses. So if, okay, I will show you this one, it is interesting. So I will switch to 1, so 10, 8, and now we will put 16 and speed back 42. So, do you check this spectrum? We have only 16 number in CPI. So check, if I will draw it in discrete, there will be 16 points. So my velocity recognition, it is not good, it is not nice, because if I will put 32, of course you can, I always make multiplication of 2 because I always use this because due to computation of FFT, it is my habit only, you can put any number that you want. You can see it is more and more detailed. So it is this one, it is C, signal to noise, no, it is, yeah, signal to noise ratio, we can try it. So is it clear that there is almost not any noise because it is sun rays 20 dB. So let me check if I will 10. You can see noise is higher and higher, but never mind, our phase is still very stable because without any problem. If I will put 0, check, unwrapping of phase. It is still linear relatively, you can see a slope. But there is mistake. Look at this. From phase is okay. My speed is 42. It should be recognizable because it is 1. But now it's influenced by noise. And what is influenced by noise? Of course, my signal. So remember, if I will compute speed from like relative changing phase of different sample, it is more and more this sample is influenced by noise, but not only amplitude, phase also. So due to this noise, by this principle we get speed 20 meters per second, but right one is 42. But speed determined by FFT, it is still right one. Why? Because I checking for maximum. And noise increasing, but still okay. So we will put -5. Okay, phase, just give up because this is definitely not linear. It is nonsense, and you can see there. Okay, 42. And if I will put -10. Okay, 42, but honestly it is on the edge, -15. Sorry, I have limitation, -10 is the lowest one. But check by the phase principle, it is already gone, it is not worth. This is not linear phase. You can try also put mind speed, and we go to 0, and slope will be, okay, I will put not 0 but 10. So what does mean that is negative or positive value? If it's slope this one or this one, it is the same. And again, you can make any combination what you want for this PRF. Can I continue? Range equation. For this, I don't have any script because range equation or power equation is about how many power I need for detection of target of this specific size that is defined by radar cross-section and some probability. So output will be 100 kilowatt pulse, 200 something, it will be just number. Sorry, I will just drink. So, just example is, determine the required power, pulse power of precision landing radar transmitter. The radar operates in 3 centimeter band in X band, so it is 10 gigahertz. You can saw it from 3 centimeter wavelength. In clear weather, it should have a range maximum 40 kilometers. Fine. For target of type swirling 2, what is mean? High fluctuation of target. RCS is very fluctuated. Swirling 0 is non-fluctuated, swirling 1 is low fluctuation, swirling 2 is high fluctuation of radar cross-section. It is done by table, you can saw it this formula. And this target type is in altitude of 15 kilometers and with an effective reflectivity of 2 square meter. It is RCS. So it is not big. Consider scanning with a side antenna, azimuth scanning, so it is continue scanning, with the target in the direction of the maximum vertical antenna pattern. What does mean? My antenna, you will be target, and my antenna just looking at you. Because of course I can look at you, but still by side lobe I will show you also. So it is just this projection. And we will neglect effect of multipath. We don't care about multipath. So max 40 kilometer, PRF 3 kilohertz, carrier frequency 9.35 gigahertz, length of pulse, noise temperature, gain of transmitter and receiver is same. What does mean? One antenna, monostatic case. Minimal detection rate is 12 dB for one pulse, probability 0.8, false alarm rate 10⁻⁶. Classic value that I presented yesterday. It is main lobe width of my antenna, and antenna scan speed is 90% divided 0.6, so you can just it is how quickly rotated. We have target parameters, swirling tip 2, independent on previous pattern, high fluctuation, target this. And my question is only one. Required pulse power for target detection. Which target do you need for detection of this? So, it is required pulse power equation, required pulse power equation in dB. So, multiplication in dB is plus, division is minus, because honestly it is so big or small values that is hard to work with this one. So, in dB is much easier work. And maximum is at 40 kilometers. So, I take care only about maximum. R is equal to R max. So, it is mean my radar is just on edge of his capabilities, and on this edge I won't see target 2 square meter size of RCS. It is all. So, from the definition of example, target is at the maximum of antenna pattern, so value of this will be 1. We can ignore it, it is 1. Multipath is not considered, so this is influence of antenna pattern, so it is 1. We don't consider that I will get reflection by side lobes. It is 1, only by main lobe. For simplification, I will see only you, not you. What is minimal power? It will be Scenario minimum. It is in definition. It is 12 dB. It is depends on what? My receiver. How is quality of receiver? KTSB. K is constant Boltzmann. T is noise temperature, bandwidth, and multiplied by 1 divided GI. What is GI? It is integration of M pulses, because we don't have only one pulses, but we have multiplied pulses in CPI. So M is PRF to M number of pulses. Integration of pulses is equal to PRF multiplied by time illumination. What does mean? Imagine that this is target and there is radar, and I will send one pulse, second, third, 4, 5, and 6 is outside of target. So I will illuminate target maybe by 10 pulses, 100 pulses. It is depends on shape. Of course, more pulses, more information, more reflected energy. It is clear. And you can see that this is also depends on speed of rotation. If I will have quick speed, okay, I will get only lower number of pulses. Slow speed, and also on main lobe width of my antenna pattern. It will be big, it will be slim. And now we will evaluate all this value. So just check it. I need compute this one in dB. Okay, so I will put the value and compute some. GI, it is integration gain, because why integration gain? More pulses, more energy. It will be 10 logarithms m in this integration gain. What is minimal power? It will be this. And what is L total? It is in our equation this. It is all kind losses. So we have atmospheric losses, but it is clear sky, so I think that we can ignore them. Integration losses, integration after detection versus coherent integration, there is some little difference. Scanning losses during integration due to shape of the antenna pattern. Why? Side lobes. Losses due to target fluctuation are processing losses. And it's not a lot of, it is not all of them. There is a lot of different type of losses, but rest is we ignore. So, and imagine we start just make computation of this one, just one equation. So this is 1, this is approximately 1, this is this value, number of pulses is 15, so on. There is individual losses computed. Total losses is about 4 dB. And my question for this one is receive power must be, or receive power is transmit power plus all these things. So of course I will make evaluation of transmit power from, and transmit power must be higher or equal to 50.5 dB watts. It is approximately 113 kilowatts. And now you know, okay, I need design transmitter that will transmit me minimally 100 in pulse, minimally 113 kilowatts, and then I can detect target with RCS 2 square meter. And I hope that will help you in case that you sometimes need it. You will just put another values and adopt it, and but it is same equation. I don't have script for this because I think that is simple for visualization. Just do it like one by one. But any system engineer start with this. What is requirement? Okay. You want radar short range, okay, until 50 kilometers, okay. And on the edge, what will be size of target that you want to detect? 100 RCS, 2 meter square RCS, it is depends on size of target, but it is clear. Okay. We will back to range quanta and Doppler sampling. Still remember? Can I go? Perfect. So we go for example for range quanta and Doppler sampling example. We will have waveform in fast time. What is linear frequency modulated pulse, length of pulse 20 milliseconds, bandwidth 1 megahertz, sampling speed 10 megahertz, carrier frequency 10 gigahertz. Range sample spacing will be about 15 meters. Pulse compressed range resolution 150 meters. Pulse train will be PRF. It is 0.2.5 millisecond. Number of pulses 128 pulses. So it is length of CPI will be 32 milliseconds. It is like some typical values. We have two targets, 12 kilometers and 14.1 kilometers with different velocity. One target goes to close to us, second just go away from -9 speed. And both targets are in different. So, what is processing chain? we form the fast slow matrix. So we just do it this one. We make fast matched filtering. It is pulse compression. What is it? Cross correlation. And columns become range profiles. Yeah, from cross correlation we know range. So we know range columns. It is range cell. It will be column, of course, but in slow time across pulses at each range bin. So it is mean there, I will compute Doppler. So it is mean that will be speed. There is some k limits, and now please run this application. Give me a second. It always run in my primary screen. And check 12. Okay, there I have a different how to say, different range. So first target is 12 kilometer, second target is 20.5, and what we can see, yeah, no problem, 2 targets. And why in Doppler spectra I see only 1 lobe? What do you think? Because both target has the same speed. Yeah, so position is different, but speed is same. Because you can see there is blue and red one, but in male lobe, blue and red one is just same. There I don't have time to finish for changing all these parameters, but I should do it. But please always go to these scenarios, and there is definition of parameters. Yes, okay, it is scenario 1, it is default. Okay, and there is range. So you can see there you can change always the value. So it is mean position of first target, second target. Speed is 0, 0, static, so it is 0 and is same. And you can slowly change what you are changing there. There you are changing in range only, range, and speed is 0, signal to noise ratio is default 0, and so on and so on. So we will pass now through all these things. This is stagger, I can close it, and we already discussed. Maybe I should update this application and put these values also to control, and it will be better because you can easily change it. But I suppose that you understand MATLAB, so you can change it even in code and not will be any problem. So it is this scenario when we have 2 targets at 0 speed. It is just first example. So second example will be that we will use only velocity. So it will be same range. Okay, give me a second. Same range. We have only low number of pulses, but never mind. But in velocities you can see that they are resolved. I have seen 2 peaks. If it's unresolved, what does mean unresolved? That we don't have enough resolution in speed. And look, it is, there is radial velocity, there is range. It is, you can see there is no resolution of targets. I see only like one target. It will be resolved. Yeah, 2 points. It is like something like this. So you know where is maximum. This is not maximum. Maximum is where is the most red one. I don't know how to say it. Purple one. Joint, it is mean different position, different speed. So you can, okay, I will reset. You can see different position, different position. One is in, we can check it. One is in 14 kilometers. I don't want this. And second is 12. And speed is 12. It is this one. X is sorry. Mine's 9 probably, something like this. There you can change it, number of sample, length of CPI and so on, signal to noise ratio. So if I will make signal to noise ratio like 10, or it will be same, mine's 20, but I am not sure if I don't have some limitation. Yes, mine's 20 is still good. My 30. Still good. Okay, uncheck, mine 40. By the way, this is usual. What is this? This is good example. What is this example? Can you see target? Yes, there is still, okay. Okay, maybe from your distance it's not so visible, but it is there. But what is the rest? It is clutter, it is noise, it is reflection from environment. And imagine, it is like before MTI, before removing static clutter, something like this. The raw radar data looks like this one. And from this, you need to find target. So, and for this reason, remove MTI, remove clutter by MTI, and then you will see, but it is depends. If will be small reflection, you will not see anything anyway. Of course, this is school example, so in real data are much more complex. And imagine, everything what I am showing you, it is just offline, but your radar must work real time. You can't stop. It will be any second, any update, any rotation and everything. And imagine that this is target and there will be close wind turbine. What's happened? There will be big red something, and definitely you will not see your small target because it is small one. So it is this one. This is some example of reduction by windowing. You probably have some experience with design of filter. You know what is window, rectangular window, and I don't know, Kaiser window, and different type of windows. Maybe not, but never mind. It is just different type of filter how you want to suppress main lobe and side lobes, some better filters. And this is this one, you could window width. So if PRF will be low, it is a good example. Check if I will make low PRF, pulse repetition frequency, distance is okay, but check why there is nothing. Because my PRF is low, so recognition of in Doppler is what is there? Blind speed. It will be mapping to this one. It will be PRF high, of course. I am outside, like it is extension of interval. SNR low, SNR high, and it is some preset that I just put for you. Group delay, just ignore. It is velocity aliasing. Okay, there is aliasing of velocity, so it is mean that my target is so high speed that can't recognize. It is ambiguity of velocity again. And if it's range aliasing, it is something similar. It will be again aliasing of range. So it is just some few presets. Everything, please, you have already discussed in scenarios. You have already discussed. And now we will go to last one. Oh, I close it. Pulse compression, just for example to have it. So rectangular, it is spectrum, since you know it, autocorrelation, but it is in dB for this reason. There, be careful, it is rectangular pulse, it is amplitude, it is blue one, and this is phase. It is red one. So I amplitude and phase characteristic to put together because for me it's better. And again, you can change duration. It will be 2. It will be and there, do you know what is ambiguity function? Okay, it is again show me on my screen. It is ambiguity function of rectangular pulse. Ambiguity function depends on time and Doppler shift. So for each range of time and Doppler shift, you will compute it, and this is cut. So cut for zero Doppler cut. So it is mean zero Doppler shift. It is our triangle, and zero delay cut. It is mean that is Doppler response. It is now our sense function. So this is 3D function, but you watch it this one like from top. This is very useful tool for analysis of quality of different type of pulses, but it's out of scope of this lecture. So you could present it, you could check it, but please check yourself this one. But I just want to show you that this is their information. So, but we go to LFM, check rectangular in amplitude, it is constant, but it is LFM, linear frequency modulation. So frequency is linearly growing up, instantaneous frequency, and spectrum LFM, autocorrelation function, and ambiguity function is displayed in another window and will looks like this one, linear. Then null FM, you can see this is non-linear, so null FM. And Barker, it is phase is hard-coded by Barker code, length 13 bytes, and looks this one. And again, ambiguity function. Looks in this one. So you have different, just different view. But I think, no, I can't do it. I just want to show you in 3D, because where is yellow, it is up, so it is complex shape, but you can present it in 3D also. Okay guys, it is all for tutorial 1. We will just finish all radar things, and now we are back in turbines. So I don't know when is planned lunch, maybe now? 1:30. Yeah, I'll check it. So we have maybe time or not? Oh, 1:30. So we have time. Ah, 12:30. Okay. Okay. I get it. So we will, after lunch, we will work with lecture 3. By the way, this one, the screen, it is hyena chabrak. I like this picture, so it is my desktop. theory. Back to wind turbines problem. So, where is wind turbine problem? Wind turbines are usually located, of course, on coast, at sea, on hilltops, on the mountains, ridge, and so on, where is very good visibility. Unfortunately, what do you think? Where is placed radar? Also need good visibility, so this coincidence, it is really serious and we need to take care about it. Wind turbines is great source of interference for our primary radar system or weather radar. It overlapping targets of interest of echoes and degrading radar sensor performance generally. And of course, if will influence like air traffic control radar, it could cause it really big trouble and a lot of casualties. So, how degrading radar sensor performance? Usually by suppress due to adaptivity false detection, so-called constant false alarm rate. Because imagine, what is constant false alarm rate? It is some constant where is decision of radar, is it their target or is not their target? And if you will have big reflection from wind turbines, then this threshold will be extremely high because there is strong reflection. So it is clear that we need this adaptivity just suppress. Also braking tracks, what this mean? You have individual detections and you follow where is your target, and now in half of the way you are just disappear target. You don't see anything due to these wind turbines. So, detection capability of PRS can be limited influence of VT by reflection of radar signals. It is major problem. Mirror reflection, it is minor problem, and our model don't handle it with this because it is not so important. And EM wave diffraction, it is shadowing behind the wind turbines. We already make analysis on this and discover that some shadowing is present, but it is not so big, so also is not included in our models. You will see later that even our model is already enough complicated, so we don't use these two things. For the development of suitable mitigation techniques, you need, and it is really necessary, need a large amount of radar data under various wind turbine conditions. And this is problem, because you can't have it large amount of data under various conditions, because imagine it is like if you have access to wind turbine and around wind turbine is in a circle some road. Okay, then I can move it and measure from different angle, waiting for different speed of rotation, but it is not possible in radar environment, because it is in environment, because there is not this road. Usually when you see where wind turbines are located, there is not accessible road, so even you don't have permission go to this place and so on. So for this reason we develop this simulator that can help you and model everything. Of course, it is simplified model. This model don't follow reflection from environment, because it is not possible modeling. It is so computationally hard that this model will never work. Of course, somebody told me few months ago, you can use some ray tracing method. In 10 kilometers per square, ray tracing method? No, I think that not exists so powerful computer to do it something else. So we need simplification model. So, and this, all these things, why we can't, all this thing leads that all mitigation techniques due to high variability needs all mitigation technique must be based on high adaptivity of these mitigation techniques. Because if you develop some mitigation technique for one wind turbine under one conditions, under other condition will not work. So, how looks received signal? How looks received signals in case that what is including or received signal to radar? You know that will be for sure some noise, always noises everywhere. It will be ground or sea clutter. It is a reflection from environment. It will be weather echoes, so it is mean it is cloud also, and it will be real targets. And plus, it will be close to wind turbines, will be reflection for wind turbines. And all these things and other things, you need to remove it before you make an exact detection of your target. And of course, you need to remove it in real time. You don't have time to make some analysis and so on. So, where you could make analysis of influence of wind turbines, you can imagine that you get reflected signals. So, how do you think that looks these signals in time domain? Like random signals, because it is summation of all reflection together and you get one-time signals. Okay, complex signals, amplitude, phase and so on, but it looks like random. So definitely you can't make any analysis in time domain. Then you can make analysis is spectrum domain, and of course we use it mainly spectrum domain. But even, how we will see later, spectrum looks like also random variable. It is not random, I must say, in advance. We discovered that it's not random, but almost looks like random. So even just spectrum in specific time is not enough. So, and if you want to see evaluation how looks this influence in wind turbines, you need spectrogram, like is evaluation of spectrum in time. So it is best thing what we discover, what is best for this analysis. About spectrogram, I just want to mention one more thing. You probably know what is spectrogram. Spectrogram is this. So each cut in each specific time is spectrum. And now you will have problem. You already know that from previous lecture that the Doppler resolution is maximum Doppler frequency depends on PRF, pulse repetition frequency. And imagine that your maximum pulse repetition frequency is some value, and maximum Doppler will be, like example, plus minus 500 Hertz. And now imagine that your rotation of wind turbines will be so high at end of the tip of blades that produce Doppler that will be 700. So what has happened in your spectrum or spectrogram? Aliasing. And it is another problem. Then you discover that you will design mitigation technique, everything, and now you want to apply to real system and discover that your algorithm stop work. Why? Because aliasing occur due to this high speed. And how you can influence? Increase PRF. But very often radar is somehow designed. It is already in an environment. You can't just change it some this input values. So this is also another problem. So there on this next two slides will be a list of negative influence. So increasing size of wind turbines, large blades and structure, of course tower also, because tower, because tower is like static object and it is caused reflection, yields to higher radar cross section, more bigger, more higher radar cross section. And you can see that we previously compute example when we radar cross section of target was about 2 meters square, and reflection from wind turbine RCS could be from 1 10 meter squares up to 1000. And it is depends on rotation, what is yield and what is the angle between PRS and so on and so on. So it is really complicated. Next problem is growing number of wind turbines. Of course, more wind turbines, more problem. Is it clear? I think. Intensive spatial expansion, because now we don't have only onshore wind turbines, but also offshore, close to coast. And where you want to see on coast, coming some plane, and it is really big area where should your radar be blind. Then we have wind farms. It is the worst scenario, these big wind farms. I will show you yesterday this Tamil Nadu area where was wind turbine every 300-400 meters for radar. This must be really terrible. Large RCS blinding radar. So it is not mean that radar not see what is there, but he see also only big target. There is big target, big red point, large point through not only one resolution cell, but through many of them. And it is not important if it's passed through this area some target or not, because you don't see. There is some stationary target from wind turbine reflection. Then identification of speed of this target is also really influenced by Doppler shift of rotating blades, because how I told you, at the end tip of the blade, the speed could be from 800 up to 1000 meter per second. But it is speed of planes. It is similar, if you can imagine. And the speed of blades is variable. It is depends on blade length and rotation speed. So this speed of at the end of tip could vary from 100 meters per second up to 1000. It is so big variability that is really big problem. Also, variable rotation. Imagine your radar looks by this, and you have all this rotation, and in every rotation will be another cross section. How you want to design and some mitigation. And wide range of rotation speed, because old one they have relatively quick rotation speed up to 15 RPM. Now these long blades, modern wind turbine, they have speed 6 up to 8. Due to longer blade, they could have lower speed. So variability of speed could be from up to 2 RPM until 15. Like example, something like this. But this depends also on the size of wind turbines. Next is variability in the turbine dimension. Of course, if I have 20 meters high tower or 100 meter or 150, it is also different. Different blade design, shape, number of blades, materials, everything this influence your radar cross section. Multipath and clutter effect, because imagine that if you have multiple wind turbines, the signal is not go just to wind turbines and back, but it is reflected to another wind turbine and back, another wind turbine. So it is multipath effect. It is also a huge problem. Also can cause it shadowing and blocking. Of course, it is clear, so you don't see what is behind the wind turbine. Frequency dependency. Imagine that you design some mitigation algorithm, everything works perfectly, we are in ideal world, but it will work only on some carrier frequency, in another carrier frequency will not work. And cumulative interference in wind farms, I already told you. So you can see all these things together. This looks like almost a random process, if you agree with me. It is so many different variables. So there I get from internet one very interesting presentation. It is from company Raytheon. It is American company that developing radars, very well known. It is US company. There you have link where you can download this PDF. It is from some conference, and check. They make analysis of two areas. The blue spots, it is reflection of wind turbines, and they combine with radar where is not any wind turbines, just for checking what is their influence. And check this. This is track. Green, it is mean it is good. I see target. I know where is target. Everything. And check the red one. Red one means I don't see target. I don't know where is it. Of course, how they know where is it? Because they have some GPS or something. It is testing scenario. But maybe 40% of track is just disappear. And imagine that will be some target that you need to know where is it. It is not good. There is different free plots because it is different heights. So 4K feet, 6K feet, and 8K feet. Of course, if you are higher, it is better. Is it clear? But imagine that you have some wind turbines close to airport when you are landing. It is almost not possible. This is another example. This is wind farms cause false air traffic. The air traffic system means that this is target, that is planes. Yeah, but it is not planes. This is showing example what's do it radar clutter. There is no any clouds on weather clutter, nothing. It is wind turbines. But it is also problem. Imagine that you send information about to planes. Okay, there is storms, you can't use this airport, you need to go to another place. No, it is wind turbines. Of course, always somebody told me, okay, so I will tell them there is wind turbines and be careful. You can ignore these results because wind turbines are static, they are not moving anywhere. But it is big area. You can't lose information about this so big area, information about this. And this is also can cause it in weather radar false clouds. It is looks like clouds, wind turbine. So there is really nice examples of different influences of wind turbines. And check this one. Another example, the green one is good detection and the red one is bad detections, lost detections. 50% in average where radar loss detection, but this is terrible. And why? Look at the location. Of course, wind turbines are on the top hill, where they should be, of course, where is good wind. I understand developers, but from radar system point of view, it is almost the worst scenario. Okay, now we move to wind turbine components. We have two main types, horizontal axis wind turbines and vertical axis. The second one, vertical, we don't consider because honestly I don't see these wind turbines in my life with vertical axis. It looks like strange shape. I don't know, do you have experience? Do you see it, this vertical axis wind turbine somewhere? I know that exists some experimental setup, but 99% will be horizontal, so of course we don't consider this vertical. And what is base wind turbines component? Foundation, okay, we don't care, it is underground. Tower, we care. It is for a static object, but this static object is relatively easy suppress. MTI filtration, moving target detector indicator. So it is clear that this is not moving and it is static. Okay, it causes a problem, but I can easily find a solution. Tower, okay, it is tower. Nacelle, it is this one. it is not so good because it is big object. I know that it's not so quickly rotating because it is slow movement. It is depends on wind direction, but still causes some problems. But still, it is quasi-static because if you imagine that we send PRI every microseconds, the movement of due to changing direction wind will be almost zero with comparison with this speed. Then we have hub and blades, it is clear. Unfortunately, blades is also very complicated shape. It is you probably saw it. I can't describe it in English, but it is very complicated shape. And imagine when your signals come, the reflection will be totally different. And it is also very, very, very hard to modeling. Because if you want model RCS really precisely, you need to take complete model of blade and use it electromagnetic wave that will compute by exactly solving solution this RCS. Good luck on 10 gigahertz. Do you know how many scatters will be? It will be millions and millions. And you need for the whole rotation, and a rotation could take 6, 8, 15 seconds. It is not almost possible to solve. You can solve for one blade theoretically in CST studio or something like this, but not in movement and so on. So this is possible approach, but not easy. So there is typical parameters. Number blades, 3, of course. It could be 4, 5 more, but honestly I never saw it. I always see only 3. So our simulator can adopt it, so you can choose any number of blades, but we always simulate it only 3 because it is majority. Then is height of tower. It could be from 40 meters to 260 meters. Length of blade from 30 meters to 100. It is typical parameters. Of course, that exists some blade that could have blade length 1 meter, really small one, why not? But we consider some typical values. Rotation speed, how I already say, from 5 to 20, typical, normally from 2 up to 20, something like this. Initial angle, where is start rotation. It is important because where you start, then from this position you know where is position each blade, and it could be any. It is a random variable. But how you will see, it is not for us important. I will describe later. And power of wind turbines, and it is vary. It is from, I don't know, half megawatts until 10 megawatts, 6, 8 megawatts, something like this. And blade tip, the movement at the end of blade tip is at maximal wind is subsonic. It will be about 1000 meters per second. So it could be sometimes even faster than wind speed. So this is really, really big problem. Okay, do you have? Now I will present you wind turbine size. We have different type of categories: small and micro wind, medium, modern utility scale, onshore and offshore. So if you can check small and micro wind turbines, it is like this. It is really pico or a really small one. Maybe you will make fun. Why I consider this? Imagine you have radar system that detected UAV. It is same size. So it is not, I know that looks like fun, this homemade or something, but it could cause it even this small problems because it is same size UAV. And imagine if rotation speed will be of this small one 40, 50, 60 RPM because it is short and very quick, it could cause also problem. Small 1.32 meters and rated power I will not read, hub height 6 to 12, residential 3.6, community and so on. So it is this smallest one. for home and so on and so on. Maybe you know this also, this small one in when you have how to say in Wild West, when you have some these turbines from it is same, and they have it about 10, 12, 14 blades from Wild West, from movies, and this one. So, but it is also a problem. It is again UAV. So reflection will be also big. And I discussed this with one person from radar company, and he told me that that even this one really can cause it RCS relatively big, that radar see this wind turbines. I almost don't believe, but it is true. Then we have medium and scale wind turbines. It is for agriculture campus and some older commercials. It is from 20 to 40, 40 to 60. It is not big one. It is older one, how I say, from 90s to 2000, when it was evaluation and starting development. How you can say even in your country start about 1990, so it is like example, good example. Then we have some modern, it is like from present time, and there I have even model examples. Vestas, Siemens, GE, another Vestas. This is relatively modern and now is used from 2020s very often. We have a lot of them even in Czech Republic, maybe even you have it there. It is like rotor has 150 meters, blades about, it is rotor and blades about 166 meters. So you can see this is to be fun. It is really large fun. And imagine this. In this area, radar is completely blind, completely. And then we have, I think that in present time, about 2020, 2023, it is the biggest one what is installed. And of course, with increasing future, it will be larger and larger. And is it clear that if they have larger blade, they have smaller rotation speed, because if they will have same speed, tip blade speed, it will be maybe more than 2000 meters per second, something like this, because it will be really huge. Then we have offshore wind, and they are bigger. Why? Because nobody cares, it is close to coast, it is undersea, and there is a lot of space, how you can see. I saw some picture close to Britain in south part, and there is some wind farm, there is hundreds of them. It is really huge wind farm. And the largest one, Vestas, it is about 236 meters with hub blade 170 meters. Imagine installation of this. It is amazing. It is great technology, honestly. So, and it is latest generation. Maybe exists some new one, but I don't know them. It is the last one what I already found. So, there is how wind turbine works. It could work synchronously, like directly grid coupled and invert based. If it will be synchronous, it is mean that they operate at relatively fixed rotational speed tied to the grid frequency. So it will be constant. If something is constant, it is easier to mitigate. Why? Because it will be still similar, how to say, properties of this, because it is constant. But unfortunately, modern wind turbines are inverter based, and since both blade rotation and inverter harmonics contribute to the clutter spectrum, and they are not synchronous, so it is causing problem, because this will be hard to predict and hard to mitigate, because it is not synchronized. And unfortunately, this is modern version. Okay, now I will show you some wind turbine mitigation approaches. First mitigation approach is turbine side mitigation. So it exists some special material that you will use and cover blades, and reflection will be almost zero. You know for sure stealth target, stealth airplane. It is same. One problem, extremely expensive. Extremely expensive. Second problem, the stealth material is not for a long time. You need to repaint it, you need to recover, and so on. But of course, for radar specialists, is good. It is mitigation technique on side of wind turbines. But can you imagine that will some developer if wind turbines you will pay for this paint? No. So unfortunately, it is not, how to say, it is nice solution, but I think that nobody uses it almost, because it, and especially from reason is price, it is really expensive. From radar side, there you can see it is plenty and plenty of different solutions. First is infill gap filter radars. So in area where you have wind turbines or wind turbine farm, it is better, you will place additional radar that will cover this area. But what do you think? It is good solution relatively, but you need to buy new hardware, and it is extremely expensive. Again, we are back. Always we are back at money. So it's really expensive. Then we can make it antenna diagram shaping. So it is mean you see antenna diagram. It is something like this. Main lobe, and so on and so on. And you will plan your antenna diagram in the way that wind turbine will be always in this 0 point. So it is mean there not will be any reflection. It is hard technique. And of course, imagine with rotation speed, or imagine with radars that is not stationary, but you can move them. You always need recompute. So it is good solution, hard to implement. Then is adaptive limitation of side lobes. It is whitening and so on and so on. I will show you later. 3D or waveform strategies, and it is about pulse waveform. You will use so complex waveform that you are sending that they pass through this limitation. You changing waveforms of radar that transmitted pulse, and from comparison of results you could mitigate. But it is very, very complex, and it is not easy implementation. It is mean you can't say, okay, so we will design one time and then we will use it everywhere. No, you need always adopt to specific place, specific parameters, specific implementation. So it is hard. Wind farm sittings or layout optimization, it is mean more organization thing from national point of view, like from government point of view. You told developers in this area you will not make wind turbines because it is close to airport or something like this. But it is good solution. But for present already installed wind turbines and radars, you can't do it anything else. But it is not bad solution, honestly. I like it, this one. It is only about careful planning. But problem is that sometimes where should be wind turbines, should be airport also. And then operational procedural mitigation. It is more about NOTAMs or ATC, air traffic control, that told you in this area, just don't go to this area, just fly around because we can't see you. Okay, it is solution, but not permanent solution. It is just temporary solution. Oh. And then is signal processing approaches, only signal processing. And of course, we develop one technique for validation of our simulator that is based only on signal processing. And we already published paper about these techniques. And signal processing approaches are unknown because every radar developer told you, okay, we have some techniques, how do it? Nobody told you how, because it is really big know-how how they do it. So publicly is almost unknown. I know only our solution because we develop and is publicly available. What is big advantage of this signal processing approaches? You don't need change hardware. It is just software. So you will update software, something like this. So it is our primary focus on this one. Okay, so and now we'll go slide by slide about one turbine side mitigation. So first we start with this material. It is radar absorbing materials, so RAM, radar absorbing materials, in blades and tower. They have steel shaping and coating scatter radar waves, so it is not mean that they attenuate wave, but the scatter wave outside where radar don't detect this signal, so you don't care that go outside. And this is same principle in stealth airplane. Yeah, because you know how looks stealth plane. It is always so different shapes. And why do you think these strange angles? Because reflection goes out and not go back to radar. So it is hardly detectable. It is only about this. Plus this material, of course, not only shape, plus materials. This reduce in very nicely about, I read some report again from Britain, and they make some analysis that reduction of RCS is 99%. It is nice, really good solution, but expensive and limited. And of course, imagine that if you want to do it for already wind turbine that already stay, you need unmounted, unmounted, everything, covered by pane and just mounted back. So it is not possible, it is clear. So it is turbine side mitigation technique. Then we have infill radar or gap filler. So it is mean that there is wind turbines, there is original radar, and you can see this is area, and this is problematic space. If you don't see there, then you put another radar infill that will cover from another angle this space and send information like to original radar or to ATC or something like this. But it is expensive. You need to buy another radar. It is special kind of radar, just infill radar, and it is just for covering some special small areas where it's wind turbines or some other source of clutter, of course. It not could be only for wind turbines. It is costly, and it also required terrain and spectrum coordination. Why? Because you place new radar, so new transmission, new permissions, everything new. And look, there is example of installation of this. It is infill radar, and there is one and second, and it covers from both sides this wind farm, and you can saw it, but expensive. It is exactly two radars. Antenna diagram shaping. It is shape of radiation pattern of the radar for reduction impact of turbines in specific direction. So in direction where is wind turbine, you will shape antenna design diagram that there will be zero. So then there is no reflection because there is no reflectivity in this direction, because antenna shape is zero. So it is adjusting antenna radiation pattern, but adjusting antenna radiation pattern is not an easy task. It is tightened with already designed antenna. So how you want to do it? If you have some antenna, you need to prepare new antenna. Or if you have AESA antenna, then it's possible, because this is more software solution how you shaping this antenna beam, but still relatively complicated. And what is problem also? Okay, in specific direction you don't see wind turbines due to fact that there in antenna beam is 0. Okay, you don't see antenna, but in this direction you don't see even target because there is 0. Okay, you mitigate wind turbines, but in case that in this direction will come to you target, there is 0. You don't see even target. So mitigates clutter, but no news radar required. It is pros, but negative is creates blind spot in nulled sectors and needs complex hardware calibration. It is not easy task, because of course if you have one wind turbines, relatively easy, you need one null. But if will be 200 of them, 20 of them, it not will be almost possible. Then is adaptive limitation of side lobes. It is side lobe control techniques which aim to prevent wind turbine clutter from entering the radar through antenna side lobes rather than the main beam. Then we have classic side lobe blanking. It is SLB, side lobe blanking. And then we have side lobe suppression. It is SLC technique. And then we have side lobe cancelling technique. And then last one is whitening technique. So it is all similar techniques that like based on side lobe operation. Advantages of this one is established techniques that can be retrofit because it is well-known techniques. It helps reduce false alarm from off-axis clutter, and they do not address clutter in the main beam. So it is good one. One SLC technique, very interesting, is patented by Intersoft patent. You can just open later this patent and check it. And nobody can use it now because it is patented, but I think that expiration is until next 5 years or something like this. Then will be publicly available because expiration of patent. I think that I check it 5 years, something like this. So you can check it later. And what is negative? May not address main lobe reflection. Effectiveness highly is geometry independent because it is side lobe, of course. All you play with is antenna diagram. And can attenuate legitimate targets. Why? Because you play with side lobes, you limitate side lobes, and if you will have target in these side lobes, you will mitigate also. And it is another problem. Any mitigation technique, if target will be close to this wind turbines, you don't mitigate only this wind turbine, you will mitigate also this target. So you need to be careful on this, especially with this null technique and all this. Okay, I can say, okay, don't watch there. But if target will be there, then you have problem. Then is pure signal processing approaches. First one is STEP, space-time adaptive processing. It is very promising method. It is adaptive filtration based on multiple transmitted pulses and multi-beams concept. It is really modern method, but I must say it is very high computational load. It is very complex and hard to design. But I think that is also one of the future mitigation technique. It is good one, but it is very hard to design. But what we'll see maybe in next 5 years is not will be so hard. It will be maybe some new optimization technique and will be easier. But it is good one. GMAP for weather radar clutter suppression. Then microdoppler signature classification. Okay, You know what is Doppler signature. If I have moving target and my signal reflected frequency will be different due to movement. But what is microdoppler? You know helicopter for sure. And imagine you have helicopter and helicopter has blades. Do you agree? So the movement causes Doppler shift. So it will be Doppler shift as you know. And what is microdoppler? Microdoppler is Doppler shift of this wind turbine. So there is like two different Doppler shift. Doppler shift from movement and Doppler and microdoppler. And why we call it microdoppler? Because this Doppler is relatively small with comparison of Doppler shift of plane, because of course it is high speed. So how you can recognize, okay, Doppler causes that your central frequency will be moved. And microdoppler means that it will change like slightly spectrum of, like it will be like jittering. And this jittering you can identify, and it is special for wind turbines. And then if I can identify, I can play with it, I can mitigate and so on. So this is microdoppler. Microdoppler, you can have it also in UAV. UAV, motion, the frequency is shifting, but you have 4 blades, like quadrocopter, you have 4 blades. And this causes this microdoppler shifts. So it is small changes in Doppler shift. It is like sawtooth, like that will be changing something like this. And what is interesting, this microdoppler is hardly to identify. Why do you think? You need really big resolution in Doppler, because it is so small shift. So you need to have a really good resolution in Doppler. But if you are able to identify, then this information even you can use for classification of target. And I saw some presentation of radar system on very short distance, like 5 kilometers or something like this, 10 kilometers, that is used for protection like nuclear power plant or some important object. And they can detect this, how to say, UAV, and even told you, okay, from this it is quadrocopter, it is this one, it is this one. And usually it is based on microdoppler signature, because each UAV will have specific signature. It is like signature, like your, exactly, or like our fingerprint. So it is like exactly, yeah, fingerprint of for this UAV. And wind turbine is something similar, if you think. This causes Doppler shift or microdoppler. It is depends how you call it. Doppler and microdoppler. Microdoppler means it is only small one, but it is also Doppler shift. What is advantage? Best advantage, no hardware upgrades. It is good one. Oh, okay, maybe some computer resources for additional software, but it is still okay. It could be adaptive and flexible. Why? It is software. I can just reconfigure, it is software, so it is easy to adopt. Quick development, relatively. Why? Because if not fit to my area, but fit to another area, I will adopt it. It is software, and any software can be relatively easy adopted, so it is okay. What is negative? High computation load. It is highly computation. You need really good computer, powerful resources for computation of this, but still it is possible. Then requires careful tuning, and this is hard, because it is like there is not any rules how you can find pure solution, because you need to tweak and founding and tweaking parameters to get the best solution for you. And sometimes small changes of one parameter cause it completely different result. So it is not easy, because it depends on many variables. So it is not mean that you found some solution, partial solution, okay, and now I will tweak very easily. No, because even small change causes big changes in this mitigation technique. So it is not easy task, but relatively possible task. And you just need software and programming skills, so it is good one. So I will tell you something about our solution. Our solution is based on DSC-based approach. And what is DSC? It is dominant spectral component. And from now you will see this shortcut DSC 1000 times. Because dominant spectral components, what could be, you know that how will looks probably spectrum from wind turbines. It will be some very complicated spectrum due to different angles, different RCS and so on from different direction. But where will be worse Doppler shift? At the end of the blade. Where is tip speed the biggest one? Do you agree? And this blade is shifted about 120 degrees. Do you agree? Because we have 3 blades, so 120 degrees. So the worst amplitude in spectrum will be from tip end of one blade, second blade, and third blade. So our approach is how detect this 3 worst component, how estimate where will be in future and mitigate. And for this we use Kalman filtration. Do you know Kalman filter? If you heard about it, I don't ask if you know complete algorithm, but you know about Kalman filtration. Mr. Kalman, it is a professor from Hungary, and I think that he died before 5 years. It is relatively new Kalman filtration. You will see, I have some slide, discovered this type of adaptive filter in 1965, 70, something like this. You will see later. So generally our approach is that we found these 3 worst harmonic components. It is mean with highest Doppler shift. We will try investigate where will be in a next sample, where will be their position, and then we design filter and mitigate just these 3 points. And you can say me, okay, what the rest? Rest is remaining, but rest is much lower reflection that end of the blades. So okay, we make reduction, not 100%, but maybe 80%, 70%, but still better than nothing, if you get my point. So
trying to draw a circle with these 3 points, like trying to draw a circle with these 3 points.
Yeah. But it not will be so easy how you will see, unfortunately, because we are working in spectrum. So you have 3, okay, I will show you 2 lines, but it's 3 lines. That constantly, because it is Doppler shift, they do it, but not regularly, and they are free. So when you do it this one, you don't know that this was first and this was second, and they are free, if you understand. Okay, this is one, and check. I will do it this one, after you don't know what is first one, second one. Plus, we have aliasing. So this goes there, and now comes from there due to aliasing. So it is almost looks like a random movement. So it is not easy. You can't say, okay, it is in, yeah, you are right, it is in circle, completely agree, but in spectrum it's not so like this. Next approach is for 3D radars, or HPRF, is high pulse repetition frequency. and waveform strategies. It is used only for 3D radars which know range, azimuth and elevation with multi-beam. And I can design some adoption algorithm, and I have multi-beam. So one beam of antenna look at this area, this area, and from comparison of the results I can design algorithm and mitigate somehow this one. But I need good resolution in Doppler, so it is mean high PRF. It is improved Doppler and high separation of clutter and targets, because you will detect these targets by multiple beams, so you can then easily separate it. But I say easily, it is not means it is easy. I can separate it, but it is relatively hard. And I must say that public solution, I don't much saw it. I heard about always somebody tells something, yeah, this exists, but nobody gives you details, because again it is big know-how. It is good for excellent clutter separation, improves multi-target tracking, negative high cost and long deployment and complexity. It is not, again, tightened with geographic position variable radar. You designing this just for like one solution for one radar for this area will works. It is not mean that is universal general solution. And with long deployment and complexity, of course, high cost, because you need to really have specialists about this one. And long-term evolution plan, because you will not develop these methods in 1 to 3 months. It will take not years, but long time. But it is promising strategy, this one. But not easy, because it is combination lot of things which you already know, of course. Waveform strategy, we know different waveform, we know what is this, we know how works 3D radar. So it is just all combination put together, but this is so many variables that is hard. Then is wind farm sitting, layout optimization, optimize turbine placement to avoid radar line of sight, leave corridors open to radar, use terrain as shielding, it is good one, requires early regulator involvement. It is for future development of turbine, it is good and relatively easy. So, okay, how to say? It is good for radar system engineers. It is not good for developers of wind turbines, because they forbidden you. No, there you can, because there we have corridor. But you get my point. It is cost effective if planned early, reduce need for technical retrofits, it is good. Negatives, not applicable for existing farms. It is main problem. And developer constraints may apply, of course. This design farm require a holistic strategy, and I don't think that this happened. In present time, it is improving, but not in previous time, because usually nobody asks radar specialist, is it involved, this one, because nobody knows that there is this possibility. But now it starts improving. I know that in Czech Republic you need to have permission if it's close to radar. Okay, how will influence? If influence, forget about wind turbines or something like this. But it is more about government problematic. Then operational procedural mitigation, sector blanking. Okay, if like I have only one wind turbine, which affect me only one resolution cell, what is most easy solution? Okay, in this one resolution cell, I will just make blank. There is nothing. Okay, I lost information from this one cell, but it is not so big loss, if you understand me. I will just suppress and tell, okay, in this specific cell, stop looking, don't show me target, ignore. Ignore, it is best word, ignore. Or another could be defined transponder mandatory zones. It is mean where planes could movement. So it is mean you will avoid place movement around wind turbines. But sometimes it's possible, sometimes it's not possible. Again, we are back. If it will be somewhere close to airport, you don't have this possibility. Adjust ATC procedures. What is mean this one? Adjusting like minimal controlled flight zone. If not, will be 300 meters. If will minimize flight zone will be like 500 meters. Okay, we are up. Is it possible? But imagine if you will apply this globally, everybody must accept it. So it is also not easy. And publish NOTAMs. And NOTAMs is like messages from individual airports which protect some area and told you don't go to this, go to this way. But it is not permanent solution. It is just solution, okay, I won't saw it them, so I told you don't go there. And make over. Okay, there will be a list of companies that I put to my list, which I found that develop some solution for wind turbines. Generally, almost all of them, they are just hardware solution. First will be Therma. They develop Scanter 4002 radar. It is this one. And it is typical example of infill radar. So you will place these radars close to wind farm. And this radar saw it in this area where it's wind farm. But you need buy this one. It is today primary radar in X-band. How you can see, range is from 80 up to 100 nautical mile. It is about 200 kilometers with resolution about azimuth resolution is under 1 degree. So it is really nice resolution. All this information, of course, I get just from website. I don't have access to this radar, so from data sheet and so on. So please don't ask me for any details because I am not customer, so I don't know these details. It is optimized for airspace surveillance and gap filter roles. So it is just additional classic radar, but some smaller one, so not classic big one, but still it is radar. It is wind farm tolerant. They have application of some special signal processing technique also. I don't know which one, nobody tell you. With strong clutter suppression algorithms. Exactly, algorithms. We can guessing. It is based on compact solid state transmitter with high MTBF and low slide cost, and it is deployed in UK in around wind farms. More information, unfortunately, I didn't found it. Because of course all radar companies are relatively careful. They always relay some data sheet, but only base information. If you need to detail, you need to ask them, and if you will be customers and you want to buy, they will tell you, but if you just want to know from academic reason, they didn't answer you probably. Second is Throughput company. They have product, call it Midas Free, and ACMS and DSMS, and it is analog clutter mitigation system and digital clutter mitigation system. So it is for analog and digital form, but it is similar. One is analog, one is digital. And check, it is not radar, it is just mitigation system. It is widely distributed small onshore wind farms under the coverage of analog, radar or digital, and solution is in the video domain. This algorithm is based on how to say, on some high-speed logic processing FPGA algorithms. I don't know details. But this is devices which you connect something between radar and visualization, make probably some setting, and this clutter from wind turbine is removed. So it is like, it is not bad solution because you don't need a new radar, but I don't know how it works in principle. Based on transition and clutter zone using color detection, but it is just general description. So, but it is a nice solution, I think. It is not bad. Then is Thales. It is one of the biggest radar companies in the world, Thales. They have Star NG and Trace NG. It is again primary radar system. This one is, I think, Star NG is 2D radar and Trace is 3D radar. It is from 60 to 200 nautical mile with good azimuth, and elevation, of course, is not covered in 2D. This radar looks like this one, this installation. And this, what I already only found, that have some special wind farm filter integrated into digital processing chain. So it will be just algorithm. So maybe this will be partially only software solution. But again, you can't find any other information. This radar use solid state transmitters, again MTI, MTD filtration, and designed for approach and route ATC with continuous updates, modular upgrades, high availability. It is like from classic datasheet. So more information is not possible to find it. Another one is Availlant. Again, it is some part of Thales. It is holographic radar in 3D continuous wave holographic radar, and it is CV radar, continuous wave. So it not works in pulse regime like send pulse, wait for answer, but it is continuous wave. It's continuously transmitting, like never ending, still continuously transmitting. But it is completely another principle, and we focus only on primary. So provides continuous 3D picture. So it is 3D, so you know azimuth, elevation, range. It is in 3D picture and don't have any mechanical rotation. So it is very, very, very interesting, this radar, and looks like this one. And this radar can separate turbines vs aircraft using some unique signature. And I have suspicion that will be this micro-Doppler signature. But I don't know, I am guessing, of course. I don't have more information. And it could be used like classic infill radar, only not 2D like in preview case, but in 3D. It is interesting solution. Next one is Hensoldt. I think that is Dutch company. It is Hensoldt ASR NG. NG, I suppose this is new generation. It is very now popular name. And it is 3D radar with integrated secondary radar. So it is primary radar plus secondary radar. And you can see it is very similar to radar that you have in Guwahati from Eldis company. This will be primary antenna of primary radar, and this will be secondary. Antennas looks always almost similar. It is for a reason, because it is from principle what you want to do. So you can see, and this black one, if you can see 1, 2, 3. It is mean that there is 3 different regime, because it is like shaping beam that's sending energy that is reflected to area and received back. So sending energy is by this 3 beam shaper or something, how to say, reflect and travel back. And why SSR don't have these illuminators? Because SSR is secondary surveillance radar, and secondary radar only receive information from planes where is this devices that just send information. Where are you? And check answer back. So there is no reflection. It is just listening time. So for this reason, there is not illumination. It is multi-beam 3D processing, exactly multi-beam. You can see this free and integration. By the way, I always told you that secondary radar asking, okay, where are you, and send back. There is 1,000 more information. It is not only about this. It is about altitude. It is about. There is even some special codes. If will be planes hijack it, then somebody just press button, and this device sent in for some special code. We have problem, we have problem, we have problem, and so on and so on. There is a lot of information. You can send, I think, 1,200 bytes or something like this. So there is a lot of different cell. It is a relatively complicated protocol, but generally for simplification like this. Then we have Indra. Indra, it is again 3D radar and 2D, 3D and 2D radar, solid state, azimuth resolution 0.5 up to 1 degree, elevation available in 3D variant, what is K-futures, advanced MTI and CFAR algorithm. So it is tailored for clutter environments. So it is mean it is works also for wind turbines, because wind turbines is another type of clutter. It is flexible architecture for S-band for approach and L-band for en route. Inherent wind farm mitigation due to use multiple pencil beams, and you can see it is first representative of multiple beams. This 3D radar, it is this 3D HPRF techniques, and I already found that already working in UK and Spain. More information, sorry I don't have it. And then is Leonardo Electronics. Again, secondary, primary radar. There is special wind farm interference mitigation algorithms. And it is all what I found about this, nothing else. It is deployed in Europe and in China. I don't know where is the installation of this radar. I don't found any information. You are lucky because you know which type of radar in India is used. 99% it is only eldest company from my city, Pardubice. Then Lockheed Martin, maybe you know this company, US company. It is, I think, one of the biggest one and very well known. This Lockheed, it is really nice, good product. It is high-end product, but of course price will be also high-end, I suppose. It is 3D long-range radar working in L-band. It is transportable, so it is not so huge. Range up to 300 nautical miles, so about 500 kilometers. It must be huge, powerful. And azimuth resolution under 1 degree and elevation also 1 degree. It is impressive parameters for so long range radar. Demonstrated capability to see through the blades. Okay, it sounds very fancy that is no masking under blades, but check these blades. Even with this rotation, if you imagine what is speed of flight when your, how to say, signal transferring, it is from 99% free space in this circle. So this masking after wind turbines, it is not huge. Problem is in exact place where is wind turbine. This, if you expect that this rotation speed will be very high, and then radar don't see anything until this wind turbine, now he can see relatively easily. He don't see like 2-3 range resolution cell so well, but after this he can see everything, because imagine this is not solid, it is just 3 blades. And it is this radar, I think that is more military, because it's used of military, of defense and NATO partners. You can't find more information because it is military stuff, so of course I don't know. Then is C-Speed light wave radar. It is low-cost infill radar for ATC application, designed to restore coverage in wind farm sector. It is just designed for wind turbines. It is nice solution, range from 20 to 60 nautical means, depending on configuration. It is 2D radar only. It is compact. Some installation is in North America and UK. This is nice solution. I think that these people also making radar for bird detection, because you know that birds are problem close to airport, because there was multiple failures due to these birds. So they have some experience for detection of this small target and all this stuff. So I think that this is some variation of this. So there you have the whole summary of all things that I already found it. It is not mean, please, that is all of them, all solution. I just tell you I don't found any other solution. So it is about this, about 2, 4, 6, 8, 10, 12 solution, 12 producer that has some information about wind turbine mitigation. Probably will be much more, but I don't know them. Okay, it is lecture 3, and I think that we could make short break. And
so break by 3:30 can we have? By that time the tea person will bring the tea also. 3:30.
okay, so I will continue with number 4.
For 15-20 minutes. I check if they is there.
No problem.
So you want what?
If you can, yes. So now I will focus in lecture 4 to general modeling approaches for radar reflection from wind turbines. It will be more about maths and about influence, what we can expect from wind turbines phenomena. This will be like introduction how we like mathematical model of like our approach of mathematical modeling, and in the next lecture tomorrow we will focus on implementation to real MATLAB model, and in Thursday we will be devoted to design mitigation, like design measurement chain, how we can measure, and on Friday I will show you complete mitigation algorithms. And of course from tomorrow we'll have lecture tutorial 2. in Thursday tutorial 3 and Friday tutorial 4, so it will be like this continue. Okay, just give me a second. I am thirsty. Thank you. So, these slides give us view about modeling strategies for wind turbine radar reflection. Just really base model is that we have scene, and what is scene? Everything what is in environment, what influence where is position of radar, where is position of wind turbines, and so on and so on and so on. So it is everything in the environment except two things, wind turbines and radar. Because wind turbines is another input for me, and another input for me, last one, is sensor or primary radar system. Our model is modular, so if you want to make extension for another type of pulse in a radar system, for another, I don't know, filtration method, anything, you just place function and you could add and adopt it easily. If you want to make some better improvement in scene modulation, also you can. So, scene is, how I already say, everything except wind turbine and radar. You could make derivation of this from simple model where is free space plus ground reflection, and we use this approach because we don't consider any digital elevation model except line of sight. Of course, it must be visible or not visible. If it's not visible, I don't care because it not influence me. But I mean this, it is, I didn't consider if between wind turbine and radar it is woods, it is pond, it is lake, something like this. Why? What do you think? Why I didn't consider this? Complexity. Okay, so we will make a break because it is first slide, so if never mind, I will continue. It is just one slide, so we will take a break and then we'll continue. I think that this lecture 4, I will have it for 1 hour and a half, almost 200, something like this, and will be done. So I little speed up. Lecture 3, it will be shortened, so we are in good way. Okay, thank you. We can shift to 9 for sure if you want. We can discuss it, why not? I will be glad because when we are finishing it is already dark, so I just want to enjoy a sun. I will not see a sun next 4 months in my country because there is only ugly weather, so I agree. If you want, we can switch it to 9. So we'll see. So please ask if it's possible. So we have about 1 hour, 1 hour 20 minutes. So I will try pass through lecture 4 and where we start, okay, where we finish about this modeling. So we have model, scene, input are scene, wind turbines, sensor, and output is radio frequency signal. It is our reflected signal that contains all reflection from wind turbine, one or multiple. But honestly, our simulator works with multiple, even wind turbines, even consider multi-part effects, but it is extremely numerically demanding, and I think that it's much better use it for designing of, like analysis of one wind turbines, because results for multiplication for multiple of wind turbines, it start be so big messy that even you can't much recognize from these results. So I will generally focus on one wind turbines. So scene, I already mentioned that is everything in the environment except the wind turbine and the radar itself. It could be vary from simple model to complex 3D model of environment. We just make free space plus ground reflection, and the ground reflection is very easily just changing of amplitudes. And wind turbine, it is complex model because it must be describe it very precisely. It is object of interest with all parameters, tower, blades, and so on and so on and so on, how you see later. And sensor, of course, it must be really careful modulated also. PRI, PRF, kind of different transmitted pulse. And then every this input, of course, I forgot in PRs also carrier frequency and so on and so on. And all this input go to model, and output is signal, reflected signal from wind turbine. And these signals in the form of IQ data, so it is like it is complex signals, IQ data. So we know information about amplitude and phase. Of course, we need both when we count in with speed, so we need also phase. So first input is scene, wind turbines, radar, then we put everything to model and we get radar echo, reflected signals. It is reflected signal, so it is in time domain. What you can see on oscilloscope, it is time domain signal. But of course, what we are using for visualization, we take these signals and compute Fourier transform and spectrogram. So spectrum and spectrogram. But we still storing a complex signals value, because you never know what do you need for another analysis. Maybe you want to use wavelet transform, something else. So we are storing signals, but all what I will present you will be based on spectra and spectrogram, of course, because there is best visualization for us. So, oh, you see well, I didn't see well. Okay, there is several category of approaching how modeling. This is not related to wind turbines. It is like general approach. So we have macroscopic view and analytical model. It is non-FEM. It is classic, and it uses simple geometric optics, radar cross-section formula, specular reflection from tower blades, and it is exactly what we are using. Physical fidelity is from low to medium, so it is, of course, don't include reflection from environment, atmospheric reflection, and so on and so on. But for discovering this phenomena, how you will see later, is not so important. It is for, so then is system level behavioral models. It is simplified representation embedded in radar simulators. It is physical fidelity is medium. Then is full electromagnetic full wave models. They are good, they are much better results, but you can take one blade and compute radar cross section in some distance. But imagine if you are doing on carrier frequency 10 gigahertz, lambda is 3 centimeters. How many reflectors you get in blade that has 160 meter? How you won't compute this one? It will be so demanding. And you will compute static reflection of one blade. And you need to do it for any movement of 3 blades. Forget. It will be better results. But I don't think that is possible to modulate. Plus, imagine that you want to modulate also reflection from environment. It is just out of my imagination how will be complex. So, next is hybrid multiscale models. It is combined macroscopic blade tower geometry with localized EM solvers. This is not bad because we just think about the update of our algorithm. Now RCS, we discovering that like we are using RCS that is unit. So it is mean every part of blade element has same RCS. It is big simplification, but we could replace this by real RCS, something like this. Because what will be? It will be some metrics of values only in specific environment. So we want to do it like this one, but okay. We want to do it like this one, but it is like future. I will talk about lecture 8. So it is general modeling approaches for radar reflection from wind turbine. And now how we continue. What is our base model parameters? It is number of wind turbines, position of the wind turbines relative to primary radar system in Cartesian coordinates, number of blades, height of tower, wind turbine blades length, range of rotor blade rotation frequencies, so how quickly, and a nacelle rotation relative to position of radar, because there is so many angles. If you understand me, you have radar, rotation, antenna. You have, how to say, you have wind turbine with respect to radar, different angle. You have blades that is rotating in different angle. And you need always compute all reflection to your blades, to your element. So there is it is very complex geometry. It is clear message. Everybody understand what we are doing, but it is so many angles, how you will see later, that is really hard to evaluate, but we have it well. So, and if you will, and how we will compute. We divided tower, we divided each blade, we divided to elements, small elements. Size of elements is variable, so we can make smaller, bigger, and this influence number of computation, of course. So if we will do it smaller, it will be high density computation, higher it will be low density of computation. And we just think that signal from radars go to each element and we compute reflection. And what will we do it after compute all reflection from all elements, and in each time instance, because it is rotation, it is movement, then we will make summation of all, at what we get? One signal. One signal that is changing in time, and it contains all information. So it is very, very complex task. also when we make tutorial 4, you will see that when you run it, even pre-process simulator and data on my laptop take it a relatively long time because, and it is pre-process. I can't work with raw data. So this is base geometry. This geometry you will see very often, these lectures and other lectures, and I will start with static parameters. Coordinate system, so position of radar, position of wind turbine in Cartesian x, y, z. So clear, I think. Then static is turbine description, individual parts. So for us, tower, rotor, and blades also, but they are movement. But never mind, you can just use it for static. What is mean that is movement? That for another time will be in little another position, but you can count it that is always static in every position. So it is individual parts. Then nacelle yaw angle with respect to PRS. And what is this? It is not this angle, this angle, this. It is this. It is this angle, if you get my point. It is this one. And imagine, this is still rotating. So this angle is changing. It is like angles in 3D. So, clear? Then for us, like generally, how works this, what is for us very important parameters? Distance. It is slant distance like in radar, classic. And this distance is not same because look, it is this distance, this distance, this, and so on, and so on, and so on. But you can compute only one. Why? Because it is static and it is not moving, it is not rotated, it is tower. So there is first optimization which we made. You will pre-compute only one because it is still same. Then we have this distance to nacelle. And this is like small circle that is rotating but never, or not rotating, but it is not important. It is like 1 point. I know that in reality it's not 1 point, but for a reason it is not important, so it is 1 point. So this distance is also static parameter. Do you agree? This is one size, and this is this distance. And now imagine that this 3 blades is rotating with some number RPM. Sorry, it is in Czech. I don't forget to translate this one. It is rotation speed, some frequency of rotation speed. And each blade is divided to blade length, blade element. And now imagine, it is rotation in time, and for each time instance, like this is 1 time, you need compute distance to this to each element. Then you will make movement about some time instance and compute completely again. And again, and again, and again, and again, and again. You get my point. It is a huge number of computation. Also, this looks like blade. It is picture. But we not consider that is blade. We consider that is tube, only tube. I know it is big simplification because the blade shape is very important, but you will see that result is not big difference from reality, and we need to do it this simplification if we want compute by this way, of course. But in future, if we will replace this blade by metrics of real RCS, if we will get this data, then we just multiply it with another number. What is RCS? It is just number. So it will be some matrix computation. It not will be something different. So this is important angle. It is this yaw position, and this angle, it is like position of rotor with respect to radar cross section. If you, to radar, if you get my point. So be careful. There is multiple angles. It is not so easy, and it is statics parameter. Then we have kinematics parameter, and it is rotational speed of the rotor. Initial blade phase, it is this angle, because we need start. And you can tell me, okay, and what you are choosing. What do you want? How you will see later. It is not so important. It will influence your results, but I will show you how you can make easily correction with your measurements, so it is possible to correct, because it is random variable. It is depends when you start measuring, and I don't know where will be this position of blades. Then is rotational speed of antenna, and it is the worst case. Imagine you computing all these distances, but not only distances. Distances only, it is parameter about distance, but what we need to compute? All Doppler shifts, all speeds of blades, for all time instants. And imagine that even this one could be rotation in the movement. So it is, geometry is relatively easy. We just computing reflections. But imagine that is all moving, even this one. So it is not mean that in one time instance I will recompute. This antenna is slightly rotating, and now it could happen that I don't see 3 blades. I will see only 2 blades, or only 1 blade, on 1.5 blades, or. And what is the worst? When make rotation, all angles will change it. So task is easy and understandable, but you need to compute. So geometry is clear. Each blade is divided to individual blade elements. Blade element represent elementary reflectivity. So we say that will be 1 or something. It is not important. It is just number. And exactly, but it is important is that we can replace this number by real RCS, because it is already there, this matrix of reflexibility. But only we just for simplification use some unit value. I don't say 1, but you understand me, some unit value, constant value. Okay, if we will have better results, it is mean some better approximation of real RCS, we just replace values by another values. But model is not affected, it is still same model. So it is good one. It is simplification of uniform RCS of these elements, because we need to do it. And it is tube, it is not definitely shape of the blade, because it is not possible to recompute. Because imagine that I even can't imagine how I will do it in MATLAB, because if I will modeling this one, it could be only through RCS. So if I will get this RCS, okay, why not? But I have a doubt that I can sometimes get it. Okay, I can get it for some specific angles, but not for all of them. For all rotation, for all combination. And of course, imagine if I will just change a rotational speed of antenna, for rotation speed of wind turbines. It is another values. So it will be relatively very complex. So calculation of position of blade elements, and now I will talk about position of blade elements with respect to radar, is based on PRF, because imagine we just talking about, and it is another funny thing that I told you about sending calculation of distance, but we are in radar. We are not transmitting the whole time, but only small part of pulse. So I need also count how long this pulse needs to get to this blade element and reflect it back, and to each element of each 3 blades, to each tower, and everything is variable in time. If will be continuous way, okay, I watching and just gathering data reflection signal, and it is relatively not easy, but easier than our case. But we work in pulse regime, so I am sending pulse and getting answer. So it is much worst case, this one. So, and another thing is that rotation speed of wind turbine is completely different from rotation speed of radar. So sometimes you see, sometimes radar antenna can detect, see wind turbines, sometimes not. So it is another thing. After computation, this slant range from individual blades element with respect to PRS, we use it computational reflected signal of all VT. Then we make summation of all signals, and result is reflected signal. But this, I call it slant range, but of course it is complex. It includes also this moving rotation, so it is this shifting in frequency, it is Doppler effect. So it is base principle of our simulator that we develop or model. I never know if I use it simulator or model, because it is just covering both. So there is a list of parameters. First one is type of transmission signals. You can use just rectangular pulse without inner modulation, with inner modulation, and so on. Honestly, we use mainly without any modulation, because it is enough. It is not so big influence to affect it of our radar signal, and it is more simplified. But it is one function. If you want another, just simply choose another function. Type of modulation or signal compression type. Again, you can use what you want. Pulse repetition frequency, it is FPRF. Carrier frequency, it is clear, it is influence our Doppler. And wavelength, of course. And in input parameters in number and dimension of VT is position, X, Y, Z, because there is, looks like it is in plane, but it is X, Y, Z, it is in, you can choose it. Height, blade length, blade rotation frequency of wind turbines, initial rotation angle of wind turbines blades, number of elements on a single blade, and rotation of the wind turbine's nacelle axis relative to PRS. It is wind direction, because of course your wind turbines always try check it to best one, so it is clear at 90 degrees, because it will be best reflectivity. So, Kenya? There is geometry. All this was related to one turbine, and now I will show you case that will be multiple wind turbine. But when I will use multiple wind turbines, we are back in radar. You know that radar has all area divided to range cell and Doppler cell. It is grid. So multiple wind turbines scenario is only if multiple wind turbine is in one resolution cell. If it will be like two wind turbines and each in individual cell, you can compute independently, completely. So it is mean if will be really close each other, then you need to compute multipath reflection, and so there is some influence. But if will be like, if we will have grid and each cell will be one, I can behavior like it is 1, 1, 1, 1, 1, 1. If you understand me, because there is not important. So it is related only if will be in one resolution cell. And then we discover that there is this combination. Imagine this is one resolution cell. And what's happened? Okay, I have one signal that check. I don't know. Okay, I will start there. This is direct signal and back signal. Direct back, it is clear. But then these signals, blue one, travel through this, this, this. And then can this, and can travel this, and all this combination. So what is number of combination? 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. So you can see color coding of combination. So it is example of combination of two considered reflection. So only I consider two reflection. We discover that dependency between 2, 3, 4, 5 reflection, because of course there can be multiple reflection, then go to radar. Forget, it is too complex, and with each reflection is signal more attenuated. So we just discover that maximum is 3 reflection, but better 2 reflection. But again, only in one resolution cell. If will be separate in each resolution cell, forget. You can behave with this simulator like there in each resolution cell is only one turbine. Why? Because you are interested only each resolution cell is independent. So I will compute responses of signal in this cell, this cell, this cells. But I don't need consider multipath because it is independent each cell. So only in case that you have more wind turbines in one cell, then you can use it multipath. And resolution in the results will be very low in the results, because honestly the attenuation is so big that I think that you can neglect it and always work with wind turbines, even like wind one. Of course, imagine if your radar will be at 100 kilometers far away from wind farm, then radar cell could be like 3 multiplied by 5 kilometers. Okay, then in one range cell you will have really big amount of wind turbines. But on other case, you will be 80 kilometers far away. How many cell will be affected on this one? 3.5 kilometer like example. Why? Because of course due to like radar cells with higher distance, it is bigger one and bigger one and bigger one, but it is still one cell. So you get my point. If it will be closer, it will be affect me more, but it will be separate in each cell. And if I will be far, okay, it will be multipath, but it affect me only one cell. Okay, ignore it. So it is like you need to think what you exactly need. So, now we go to influence of wind turbines on radar spectrum spectrogram. Due to high range of tip peripheral speeds of individual blade elements, there could be speed from 0 to, of course, when it's shut down, to 220, 240 meters per second. It is about 800, 900. It is just speed of classic plane that I arrive. It is classic, it is about this speed. So, receive Doppler spectrum components caused by blade elements reflection occur within the entire equivalent range of blade element speed. And we will go to this one. Imagine that you have 5 rotations per second or something like this, or per minute. It is not important. What will be speed of this one? Relatively low. This one higher, this one higher, this one higher, and so on. This one very high. So it is increasing. So it is mean Doppler shift of this will be low. This will be higher, 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 higher to some maximal, because there is maximum speed. Is it clear? And what will be results? Results will be that in spectrum or spectrogram in time will be all Doppler shifts, because you will make summation, because it is one reflection surface. But each element rotation with a different speed, plus pulse transmission, plus rotation of radar. And all you need to compute well, and results will be one signal. So, the spectrum components highly variation in time, highly vary in time, because there is almost all components caused by this Doppler shift, because there is almost all frequencies due to this fact. Of course, it is clear that some has higher amplitude, lower amplitude, and it is variable. And on which depends on it. Also on, how to say, this radar, it depends how is. If it will be like this, and this is radar, the distance to each element, even through rotation, will be constant, because it is circle, so it will be constant. So how will looks spectrum? 0, just tower. And if it will be like this, the speed will be maximum, because you understand me. And if it will move like this or like this, so it will be maximum, and you will see the biggest Doppler shift. And everything between, it will be something. So, each element move with different instantaneous radio velocity, I already told you, and Doppler spectrum of the turbine is spread over the wide range of frequencies. It is important message. And of course, I already told you what will be biggest influence. End of the blade tips. This one, of course. The biggest piece, biggest Doppler, biggest amplitude. And it will be for case that is like this one. And also change distance, because if I am there, distance is like this. If I am there, distance is only this. So this is 0 Doppler shift, this is maximum Doppler shift, and everything between. So we discovered that there is 2 main phenomena in the spectrum domain. First is dominant spectral component, end of the blade tips, and it is our primary focus for mitigation, because you can't predict the whole spectrum of each element. It is not possible. So we from this all range of elements and all range of Doppler frequencies caused by this movement, we just make simplification. Okay, what we will do it if we will just mitigate this three biggest one, and not only exactly these three values, I mean some small range around these values. It will help us, because this small around nutshell, it is small rotation speed, this not cause it so big problem. It is almost static, if you understand me. Some small plus minus 2-5 hertz of Doppler shift, okay, MTI filter, we will handle it, it is not so important. So, dominant spectral component is clear now. What is it? It is the end of the blade tips because due to high speed. Then we have flash. Flash is strong short duration events when blades are aligned specularly with the radar. What is mean? Radar sending electromagnetic wave. It is wave. It is wave. And imagine sometimes happen that blade position and this electromagnetic wave will do it this one. Like each element will be reflected with maximum intensity, if you get my point. It will be exactly right position that will be like maximum. And this we call it flash. And what do you think? How will look this spectrum in case that just flash occur?
It will look like something is detected target.
It is all looks like target. So no. It will looks like the whole part of your spectra from zero frequency to maximum Doppler frequency will be maximum. It will be like constant maximum. So it is mean you don't have chance to do it anything with this. Why? If I will mitigate this flash, I will mitigate everything what is inside because it is maximum. So, but I have good news. This flash occur only about 5% of time during operation. But during this time, forget, you don't see. But it is for like approximately 1 up to 2 milliseconds. Good. It's not so bad. But how you can recognize something when is whole spectrum saturated to maximum? You can't recognize anything. It is so saturated because each position, due to each position, you get maximal reflection, and all this reflection just go back to radar. So, and this phenomena is flash. We ignore this flash. Even if we model it, we could model it, we try it. It is not for mitigation. I can say during this flash, ignore, because I can't recognize. It is not exist any type of target that will beat this flash, if you understand me. It is so high, so it is not necessary to model and work with this because you just need to ignore these flashes. But during rest of 95%, 90%, you can mitigate this DSC component, but it is only 3 of them. So we make simplification from 1,000 and million of them to 3 of them. And this is possible to modulate. The biggest contribution on this has my friend and colleague, Dr. Karel Jurica, that he worked on this on during his PhD studies, and he, like majority with me, developed this model. So I just want to mention that is, of course, not only my work. It is this discover of DSC component is his work. And there is example that now we will talk about dominant spectral component, and it is this is example of spectra. First rotation, second rotation, third rotation, 4, 5. Imagine that you have radar and start rotating. And always I see wind turbines only through some short period of time. So it is spectrum of first time, second time, during second rotation, third rotation, fourth. And check this one. Do you see any prediction of this? It is look like random. And where is this DSC component? It is first blade, second blade, third blade. First, second, oh, I lost it blade. Where is it? Probably covered by tower. First, second, third. First, second, third. First, second, third. You can see they are still moving. They are still moving and moving due to this blade speed and with different position and so on and so on and so on. So is it clear, this description? Normally you should see always 3 maximas plus on 0 Doppler you will see stable maximum. What is it? Tower, reflection of tower, 0 Doppler. I don't care, MTI filter is enough, it is static. So I can easily remove this one. It is same like this one. But check rest. Do you see any periodicity? No, in spectrum. This is example of this. These 3 points, it is 3 these points. With, if I will move in spectrogram, like example this, it will be like second turn. If I will move to 5, it will be 5. It will be this one. Do you get my point? So, this red line didn't exist. It is just visualization for better visualization. But do you see in spectrum looks like random movement? But check there. One sine wave, second, third. It is 3 harmonic signal. Why? 3 blades. What is angle difference? 120 degree. It is classic example that you can relatively easily simplify problem of almost from infinity reflectors. Okay, so if I will how to say, if I will mitigate these 3 sinusoidal frequencies, then rest is relatively low. And what this mean? If there will be target, I will see amplitude. So there is no issue. So I need to mitigate this 3 plus tower, but tower is not problem. So it is our mainly Karel Jurica contribution in with founding that this is quasi-periodic movement, but we can found it in spectrum, but later when we found it spectrogram, you can see, yes.
So they are not symmetric because of the shape of the blade.
No. Imagine that this is one maximum, second, third maximum. If you will make cut like this, maximum 1 will be there, second and sorry. If you get my point, if you will make cut, then values is always there is cross section of this red line. So it is like you have 3 harmonics waves and always make a cut. So it is this 3 maximum amplitudes because there is spectrum. but spectrum in time. So each cut is one spectrum, from 0 up to 20 rotations. So it is first spectrum, second, and so on. And one thing, it is relatively hard to understand what is this cross. Okay, this is spectrum, but what does mean? You told me that this is amplitude, right? But what I have on this axis, Doppler, it is amplitude, but units are hertz. If you get my point, because it is this values. It is like this is amplitudes, of course. There is specific Doppler frequencies, and I need to mitigate this one. You will see later when we do it, this mitigation technique with UKF filtration. So these three hills in each spectra is strongest DSC component that we want to mitigate, and we call it the dominant spectral component. And if you will mitigate this one, then will be some rest of this between the maximas. And what is this between maximas? It is reflection of different blades element, but their contribution is lower. Why? Because they have lower speed. It is not, and they have so not bit reflection. Only this, they at the end of speed is the end is reflection. So instead, we won't try to modulate the whole spectrum. We ignore it. We won't modulate movement of these three maximum components, DSC component, and if we will do it and we know how it works, then we could make mitigation technique how remove it. So is it clear? This is the same I want to show you. It is like Doppler spectrum at time 0, and you get tower, one blade, second blade, third blade. So you can see, and this reflection where will be position depends on mutual angles, how I already explained. So this you can see these individual points, and there if I will mitigate this place, this place, this place, this place, this is relatively in a similar level like others, like noise, spectrum of noise. So it is mean that my target not will be masked. I need to remove only this part, these three parts from spectra. It is also not so easy task, but still, it is not so complex. So can I continue? So DSC component is so random. It is periodic or quasi-periodic and tightly linked to mechanical rotor speed, of course. Because if rotor speed will be higher, what's happened? This maximal side of Doppler will be higher, and they will travel through higher distance, like this contribution movement. Why? Because it is higher speed, higher Doppler, so it is clear. And the tip blades, each wind turbine blades rotates with some angular velocity omega r in radian per second, of course. Angle per second, it is changes its angular velocity or radial velocity. I don't know which version you use it. So this radial velocity could be described like angular velocity multiplied by r. What is r? blade of length multiplied by cosine function omega RT plus phi 0. So what is this one? Initialization angle. And so it is like free blade system. 120 shifted. So first blade, second blade, third blade, ABC, they have like this behavior. Doppler spectrum produced will be FDT 2 VR divided lambda, so it is this one. You can see, and we are in Doppler spectra. And this we want to try modulate. But now looks that is not so complicated, if you get my point. So each blade tip generates one sinusoidal Doppler shift. The total reflected signals becomes a sum of the three sinusoids phase shifted by 120 degrees. And what is the best one? It is almost identical to the three-phase sinusoidal system in power engineering. It is the same. And it is probably very well known for you. So there I just put physical interpretation of analogy. Of course, it is not same, but everybody knows this three-phase sinusoidal system. Everybody use it. And influence of wind turbines for radar is the same. So we have rotating three-phase magnetic field, induced voltage 120 degree. We have rotating three-blade rotor, produce three-phase shifted Doppler modulation. Same. Similar principle, same principle, not same, of course. Electrical output is sinusoidal voltage. Radar echo modulation is sinusoidal Doppler shift. Okay. Harmonics appear if magnetic distribution is not uniform. Harmonic Doppler components appear due to geometry and blade asymmetry. Same. This three-phase voltage are sinusoid shifted by 120 in time. Three blades is separated by 220 in azimuth, and the three tip signals are again phase shifted by 120. So it is free voltage analogy. And everybody knows this analogy, so it is easy to understand. We always need to figure out how to explain people easily. And okay, it is free phase analogy, but it is true. It is true. So, and what is good, it is relatively periodical. Of course, I maybe better use quasi-periodical. It is periodical, but there is some little differences due to different RCS because we don't modulate exactly well. But it works. So, can we use this periodicity of DSC for mitigation? Yes, because it is periodic. And if it's periodic something or quasi-periodic, because what's happened if I will slowly start changing speed of rotation of blades? What do you think that happen? The sinusoidal frequency or period will be shortened or longer. So okay, there will be some breathing, how I say it, but it will be extremely slow in comparison of transmitted pulses because it is just milliseconds. But I discovered that starting time of wind turbines from 0 to some nominal rotation speed in modern cases is about 10-15 minutes. And with sending milliseconds, microseconds, it is for us is almost constant. And if it's something almost constant in period, okay, I can predict where will be in the next time and next time and next time. And if I can something estimate or predict, I can design filter and mitigate. So, and why we focus on this? There you see picture without this red line only, because this is like example to understand well. Result is this one. So you can see that this is biggest values, of course, and Why I want mitigate this biggest one? Because there will be masking of target. But why not there? Because there not will be so big masking and I can relatively ignore in the rest. And what is mean this area? It is this area or this area. You understand in this area. Oh, of course, there will be some influence. I don't tell that not will be. Yeah, it is, but much lower. And it is possible that very weak target will be masked, still will be masked. But some bigger one or middle one, it not will be masked and I will show them. So my task is relatively done. Okay, I design something what relatively works. And few words about flashes. Do you see this? There is still sine wave. Do you saw it? 3 different sine wave. And one time, like typical time duration of flash is 1-2 milliseconds. And during this period, all is in the phase reflections, and you see just full spectrum. How will looks there? It will be like constant, full spectrum. You can't do it anything with this. Okay, I can ignore or mitigate, but I will mitigate everything because I can't recognize what is useful information, what is not useful. But just stop thinking about this because it is, you can't do it anything. So during these times, it is true, mitigation algorithms failed. I don't know how other companies, maybe they have some solution, but I have doubt about it because how you can recognize something what is 1000 stronger reflection than your target. I don't think that is possible even. But if you lose connection with your target for 1 millisecond, 2 milliseconds, never mind, because you have tracking algorithm, so it is mean they predict movement of target, and target can't move like in one way and after 1 millisecond to another way. It's not possible because it is plain. It is not any huge, even helicopter can't do it this quick movement. So it is clear that I never mind during this flash, I still have my tracking algorithms that during this short period where I don't know anything, they will cover because they predict where will be. It is just prediction, it is true, but never mind. Okay. The observed turbine spectrum, this spectrum what I already show you, it is not influenced only by wind turbines, but by a lot of radar parameters. And we are again back, and for this reason I need make lecture 2 for you about this radar, because consequence of limited sampling frequency causes Doppler effect, aliasing of Doppler effect. And it is done by PRF or PRI, inverse value of PRI. And again, we are back. If I have PRF with some setting, and my maximal range of Doppler will be 1 kilohertz, and Doppler speed caused by wind turbines tip blades will be 2 kilohertz, I have problem. Because there occur aliasing, and what's caused this aliasing? That this with higher rotation frequency, this so-called amplitudes, sine waves will be higher, 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 and when I reach maximum, then not continue like this one, but this copy will be aliased to this one. Because it is aliasing copy of spectra. You know probably what is aliasing. You are working in spectral domain. little, no? But you understand me, it is like mirroring. You are outside of range, you have range, some range. And if you are outside, this will be copied to this, to same, like if you have minus 1100, it will be 900 in this case. Always it is wrapped to same region. It is sampling theorem, but you know sampling theorem. It is same. Sampling theorem. If you, I don't know, as example, my voice have maximum frequency 20 kilohertz or bandwidth 20 kilohertz, how you need to sample? Double time, 40 kilohertz. And if I will undersample, aliasing occurs. So all this higher frequency will be mapped to my base frequency. And it is the same. It is completely the same. This amplitude will grow to maximum and then should continue, but due to my limitation, this will be mirroring to the same in same time, but it will be happen there. And this aliasing is little problem. Why? Because when occur aliasing, it is no more sinusoidal wave, because it is due to aliasing and due to reflection. And in this case, the mitigation method, of course, will have little problem. But honestly, this not happen very often. Why? Because rotational speed of your antenna, it not will be always maximum Doppler shift. It is happen some time by time only, due to worse scenario, how I can say. So it is not so big problem. And again, if you design good filter, like Kalman filter, nonlinear Kalman filter, then Kalman filter is relatively robust to handle it for some time, of course, only for some time. If then this will still continue, this error, you will have big problem because Kalman filter failed and can't predict these values well, and what's happened? Okay, DSC component are back. But we make analysis and it was relatively enough stable. Okay, it is about this Doppler speed. I already show you. No, I didn't show you. It is dependency about aliasing. Imagine it is influence of the carrier frequency on the chain in Doppler frequency at different radial values. If I have, like example, 10 gigahertz, then in 10 gigahertz speed of target 1 meter per second cost me Doppler shift about 70 hertz. 5 meter per second about 220 and so on. So you will make cut and you will see. But imagine if I will have if I will have only 100 megahertz. So what will be? How will be Doppler shift on 26? It will be 10 megahertz. What will be Doppler shift of this one? Oh, we are out of range. We can't recognize it even. Why? Because we have too low carrier frequency. So of course, and it is this aliasing, how is converted back. So higher frequency give us very good sensitivity on low velocities, but they suffer from Doppler ambiguities. And again, we are back. We do it during the whole morning, during tutorial and yesterday. So lower carrier frequency, higher unambiguities, it is better, but low sensitivity to low target velocities. It is against. Okay, you have low unambiguities, but for low speed will be bad. If for low speed will be good, you have ambiguities. And again, you need to find some balance between this one. So you can see that this is really dependent on radar parameters. And it is about aliasing. I already told you. I think that I must skip. So I just this end. PRF must be high enough to cover the expected blade tip Doppler frequencies without aliasing, but still low enough that we maintain a reasonably unambiguous range in distance. But it is terrible requirement because goes each other. On one side high, on other side low. So it is hard to balance. And you need to understand that sometimes you can't even change PRF in radar. You can usually, but only in some small range because it is designed for this type. Okay, I think I know that still will have some free time, but I would like stop now because there will be the wall block that is related together and I would like to finish tomorrow if never mind. But yesterday time delay, I think that we relatively catch because I speed up number 3, so I have only 20 slides missing today, so it is not much, so we will continue morning. And do you think that you won't start at 9 or 10? It is up to you.
I had asked the coordinator of this.
And it's not possible.
So regarding the schedule of shift also, he said that he has sent the schedule to IIT Hyderabad, but we will manage in that shift. But 9, I think maybe it because it's getting online link also.
Yeah, okay.
So 10, exact 10 will be okay, sir.
Okay, so exact 10 we will stay on this, no problem. We just make reduction of this 2 hours gap. It is okay.
We told that we have forwarded the schedule to the IIT Hyderabad.
Okay.
But that is possible. That lunch we are shifting 1 hour and the last 1 hour we are managing.
Okay. So we start at 10 like usually and we'll continue, but it will be not 2 hours lunch but only 1 hour lunch, and it will be better and we can go about 1 hour earlier and I fulfill my duties. Perfect. Thank you very much for your attention and we'll see each other tomorrow. Thank you.